Hello everyone and welcome back to General Chemistry. In this video we're going to go from 2D to 3D. So let me pull up the rules that I had listed in the previous video for drawing Lewis structures. I would hope that you practiced enough since the last video to actually be able to draw your Lewis structures without needing to look at these rules, but there they are in case you need a refresher. Okay, so I guess I'm not going to put this up on the screen again, so I guess if you really need these rules to be up in front of you, open this video and have it paused on this list in a separate tab, or take a screenshot of it, or whatever you have to do. But we're just going to move on. So going from 2D to 3D, first thing I need to show you is a couple of basic geometries, a couple of basic shapes that we'll be talking about as we describe the shapes of different molecules and polyatomic ions. Okay, so here are a couple of basic shapes. I guess you could call them the family representatives, and I'll get to what that means when we look at the bigger chart that has all the shapes. But yeah, you have 5 basic shapes to consider, and we'll look at molecules that either have these shapes or are a slightly modified version of one of these 5 shapes. So you've got the linear shape where all of the atoms connect in a line. You've got the trigonal planar shape where if you connect the atoms they make a flat triangle. You have the tetrahedral shape, which is kind of like a pyramid, except it doesn't have a square base, it has a triangular base. You've got the trigonal bipyramidal shape, which is basically 2 pyramids connected bottom to bottom, 2 triangular pyramids to be specific. And then you've got the octahedral shape, which is like 2 square pyramids connected bottom to bottom. So those are the 5 basic shape families that we're going to be discussing. If you want to look at some of the modified versions of those 5 shapes, then I can show you the following list. Okay, there it is. Okay, so in the linear shape, there's only one variant, which is the linear shape. The trigonal planar shape, if you have 3 atoms connected on the connected to the central atom, then you're just going to get a flat triangular shape. But if you have 2 atoms and a lone pair, then you're going to get this sort of boomerang shape, this bent shape, or a V shape, made by just connecting, the atoms themselves. In the tetrahedral family, that's the 3rd row of this chart, you've got, of course, the tetrahedral shape, but you also have the trigonal pyramidal shape, which will look kind of like a pyramid with a triangular bottom. And you've got another type of bent shape, where 2 of the atoms in the original tetrahedral shape are replaced with lone pairs, and then you've got the remaining atoms make up this sort of V shape, this boomerang bent shape. 4th row is the trigonal bipyramidal family of shapes. So of course you've got the main representative, which is the trigonal bipyramidal shape. But you also have something called the sawhorse. It's also called the seesaw. You will see why later on when we actually get to a molecule that has that shape. I've got my 3D modeling kit with me, so we'll actually get to play around with this stuff and see what it looks like from all angles. You also have the T-shape and the linear shape are possible variants of the trigonal bipyramidal family. The octahedral family has 5 different variants, which include, of course, the basic octahedral shape, the square pyramid shape, the flat square or square planar shape, the T-shape, and the linear shape. I've never encountered any molecules that are in the octahedral family and have the T-shape or the linear shape. I've seen the T-shape and linear shape in the trigonal bipyramidal family, but not the octahedral. So I don't expect to encounter that, but there you go. Those are all the possible shapes that we can get. I'll be pulling this thing up frequently as we go through all of the molecules and ions I have ready for us. So, without further ado, let's get started. We're going to draw a bunch of Lewis structures, and we're going to revisit these Lewis structures. So I think I'm going to leave a lot of empty space for these because we're going to need to go back to them and fill in some other details later once we get to talking about, you know, some other properties of these molecules. Anyway, first up I've got my HCN molecule, hydrocyanic acid. And I guess, let's see, I think I can do 4 per page. I think that will work just fine. So let me split the page ahead of time. Yeah, I'll do HCN there. So, central atom, what's it going to be? It's going to be carbon because it has the highest valence. So carbon is the central atom. Connect a single bond to hydrogen and a single bond to nitrogen. Hydrogen does not need an octet, but otherwise give all your guest atoms an octet. And if you don't know what I mean by guest atoms, go back to the previous video. It's not an official term, but it's what I like to call them. Okay, tally up electrons used versus electrons available. So we've got 1 valence electron from hydrogen, we have 4 from carbon, and we have 5 valence electrons from nitrogen. 1 plus 4 plus 5 is 10, and I've used 2, 4, 6, 8, 10. I've already used all 10 electrons available, and the central atom has less than an octet, so I'm going to replace this lone pair with a bond, and I'm going to replace that lone pair with a bond, and there you go. I guess I'll redraw it for clarity's sake. It's hydrogen single bonded to carbon, triple bonded to nitrogen with 1 lone pair on it. Okay, and what shape do we have here? Well, in this case, I've got, let's see, I've got 2 electron domains around the central atom. So let's define electron domains. All of the bonding geometries that we're going to determine are going to be determined based off of the central atom. So what we really need to do is figure out how many regions of space around the central atom contain electrons. And in this case, the carbon has 2 electron domains, 2 regions of space surrounding it that are full of electron activity, you could say. You've got to the left, you've got a single bond which has electrons moving around, and to the right, you've got a triple bond which has electrons moving around. So 2 regions. The fact that this is a triple bond doesn't matter. It still counts as just 1 electron domain, 1 region of space around the carbon that's full of electrons. So this thing has 2 electron domains, and both of those electron domains are bonding domains. There are no non-bonding domains on this carbon. Non-bonding domains is just another way of saying lone pairs. If I had some double dots on the carbon, then I would claim to have non-bonding domains, or lone pairs if that's what you'd rather call them. Okay, so I think this one is pretty obvious and easy. It's the very first one. It's the linear shape. You've got 2 regions of space around the carbon, and 2 regions of space is just the first row. It's the linear family, which only has 1 representative. So we can say that the electronic geometry, or electron domain geometry, is linear, and the molecular geometry is also linear. So electronic or electron domain geometry is linear. Electronic geometry or electron domain geometry is linear, and the molecular geometry is also linear. Some of you might be asking, what's the difference between electron domain geometry and molecular geometry? Electron domain geometry is basically which of the 5 basic shapes does the molecule belong to. It depends solely on the total number of electron domains. It doesn't matter how many of them are bonding domains. It doesn't matter how many of them are lone pairs. The molecular geometry is the shape based on just the atoms and not necessarily the electron domains surrounding the central atom. We'll start to see the difference more clearly as we look at more of these. So let's actually move on to the next one. So next one on my list is the sulfite ion, SO3 2-. SO3 2-. Okay, so central atom is going to be sulfur. Single bond each of the oxygens. Give each guest an octet. There we go. Now each oxygen has a total of 8 electrons surrounding it. And tally up electrons used versus electrons available. Sulfur has 6 valence electrons. Oxygen, we've got 3 of them, each bringing in 6 valence electrons as well. The ion as a whole has a -2 charge, so that means we've got 2 more electrons than what we bargained for. Okay, so 6 plus 18 plus 2, that's 6 plus 20 is 26. So let's see. 26 electrons available, and we've only used 8, 16, 24. We've only used 24, so the 2 leftover electrons get dumped onto the central atom. All unused electrons get dumped onto the central atom. Central atom has an octet, so it's good to go. We don't need to do any double bonding or triple bonding. Okay, how many electron domains are there around the central atom? We've got 4 of them. A bond here, a bond here, a bond here, and a lone pair here. So 4 spaces or 4 regions of space around the sulfur that contain some amount of electrons. How many electrons doesn't really matter. But yeah, we've got 4 electron domains. 4 electron domains, the electron domain geometry, or electronic geometry for that, is the tetrahedral geometry. That's the 3rd row of that table. The number of, they called them electron dense areas, but I call them electron domains because I don't think that asking students to learn the word domain is too much to ask for. Unlike some people who I guess like to dumb things down and they think they're helping students. I argue they're not, but let's push that rant aside. Back to the point. So electron domain geometry is tetrahedral. what about the molecular geometry? Well, we've got one lone pair. So in the tetrahedral family, when you have one lone pair, the remaining atoms make the shape of a triangular pyramid. That's the trigonal pyramidal shape. So electron domain geometry, or electronic geometry, is tetrahedral. And the molecular geometry is trigonal pyramidal. Trigonal pyramidal. Trigonal pyramidal. I don't think I can fit that all in there. Let me write it down here. Pyramidal. Okay, there we go. And let's actually see what this looks like in 3D. So what I have here is a 3D modeling kit. It's typically used for organic chemistry, but you can also use it for inorganic chemistry if you want. If you want to buy one of these, you can buy it at the Darling Models website, darlingmodels.com. You can also go to molecularvisions.com to buy one of these. They're like, I think I bought this for like 20 bucks. But yeah, inside this kit you have a bunch of pieces that you can put together, kind of like Legos in a way. And yeah, for the tetrahedral shape, what I'm going to do is pick up a pair of these. I guess they're designed to have a 109.5 degree angle. Connect them together. This is the basic tetrahedral shape. I think you'll have an easier time seeing it on a white background. But yeah, that's the basic tetrahedral shape. And then if one of those four legs, you could say, is instead of being an atom, it's a lone pair. I'll use one of these red marker balls to represent a lone pair. Then, since electrons are small, if you have a lone pair here, you see something that's tiny, so basically it's practically invisible. So if I were to just kind of cover up the lone pair, what I have left, if you kind of imagine connecting all of the points, all of the vertices together, what you have essentially is the shape of a triangular pyramid. Hold on, is that angled right? Yeah, if you try connecting those vertices together, essentially they just make a flat triangle at the bottom, and then on the sides you see a bunch of separate, I guess, side triangles. So you make a triangular pyramid with that shape if you ignore the presence of the lone pair. Since lone pairs of electrons are much smaller than actual atoms, it makes sense to ignore them to see what the overall shape made by the atoms is. Anyway, off to the next one. Next one is, oh, I almost forgot. Brackets. This is a polyatomic ion, so I need to put it in brackets and show the charge. We'll pretend that the bracket reaches all the way around it. But yeah, there you go. Anyway, next one is SF4, sulfur tetrafluoride. I think I know what shape this is gonna be. So SF4, sulfur tetrafluoride. I didn't leave space above it. I guess I'll just tally electrons below it. But yeah, sulfur is my central atom. And then I've got 4 fluorines connected to it. And if my prediction is correct, I'm going to end up with a lone pair on the sulfur. But yeah, let's give each of these fluorines an octet. And then let's figure out our running tally. So sulfur tetrafluoride. Sulfur brings in 6 valence electrons. Fluorine brings in 7, so 4 times 7, since we've got 4 of them. And we don't need to add or subtract anything to account for charge. So 6 plus 28 is 34. And we have used 8, 16, 24, 32. We've used 32 out of 34, so the remaining 2 get dumped onto the central atom. The central atom, does it have an octet? Well, it has more than an octet, so nothing we can do about that. We leave it as it is. Okay, how many electron domains are there around this central atom? We've got 4 bonds and 1 lone pair. 4 bonds and 1 lone pair. So that's a total of 5 electron domains. Which family does that belong to? If we look at the 4th row of that chart, we see that 5 electron dense areas, or 5 electron domains, corresponds to the trigonal bipyramidal electronic geometry. And as for the molecular geometry, we have 1 lone pair. The 1 lone pair version of the trigonal bipyramidal shape is called the sawhorse or the seesaw, and you're about to see something really amazing about why it's called the seesaw. But let's flip back to our camera and let's write down the electron domain geometry is the trigonal bipyramidal shape. Trigonal bipyramidal. And the molecular geometry, maybe I should have done 2 molecules per page instead. The molecular geometry is the seesaw or the sawhorse. I've always known it as the seesaw, but apparently sawhorse is also an accepted name for it. I don't know, maybe sawhorse is used by Europeans and seesaw is used by Americans, or something like that. I'm really not sure. I have no clue where sawhorse comes from. But yeah, why is it called a seesaw? Prepare to be amazed. So I'm going to take a 180 degree bond and a 120 degree set of separated bonds, and if I put those together, then I get, wait for them to snap, there we go, I get the basic trigonal bipyramidal shape here. This right here is the trigonal bipyramidal shape. If you connect all of the ends of the, I guess, legs you could call them, or arms, then you can probably see how they connect to make these triangular pyramid on this side, and then if you flip it over, another triangular pyramid. So yeah, they're like triangular pyramids connected bottom to bottom. So if there's 1 lone pair, if one of these edges is replaced with a lone pair, I'm going to use a red marker ball to represent a lone pair again, then you get this shape, and this shape is called the seesaw because, well, it is a seesaw. I suppose it might be harder for you guys to see from my camera's angle, but if I hold it sideways a little bit, maybe, can I do that? Well, if I hold it like this, maybe you can sort of see how it's like a seesaw slash teeter-totter that can just tip over side to side. So yeah, you can have all sorts of fun with this shape. It's a seesaw. And there's where the name comes from. As for the sawhorse name, I guess because it also resembles a sawhorse, which I had to look up. Apparently it's something that you put things on when you're sawing wood or something like that. I don't remember. It's been a long time. But yeah, that's the seesaw shape. Let's move on to our next item. Next up, we've got PF6 minus. Next up, we have PF6 minus. Maybe this is called the phosphorus hexafluoride ion? I'm not sure. You'd probably find the rule for naming it in one of the IUPAC color books. I'm sure I mentioned it before in a previous video. Was it the red book or the blue book? No, I think the blue book is for organic chemistry. It might be the red book. Anyway, PF6 minus, phosphorus is obviously the central atom in this case. And we've got, let's see, 6 fluorines to connect to it. Maybe I shouldn't make these bonds so long. Maybe that's why I'm running out of space. But I don't want it to look too crowded either. Okay. There's your 6 fluorines, and of course, give each of your guest atoms an octet. Unless it's hydrogen, of course. All right, tally up electrons. So phosphorus has 5 valence electrons. Phosphorus normally has 5 valence electrons. Each fluorine brings in 7, so that's 6 times 7. And the negative charge tells me that I've got 1 more electron on top of what the atoms normally come with. So 5 plus 1 is 6. 6 plus 6 times 7 is 6 times 8, which is 48. And I've used 48 electrons because 8, 16, 24, and then another 24 there. That's 48. So no leftover electrons to dump on phosphorus. Phosphorus already has more than an octet, so we're done. We're done with the Lewis structure. Well, almost done. Brackets. I'm probably going to be forgetting those a lot. Whenever it's a polyatomic ion, use brackets and put the charge on the outside. Okay. So, what shape do we have here? Phosphorus has 1, 2, 3, 4, 5, 6 electron domains surrounding it. All of them are bonding domains, no lone pairs. And if we look for the family that has 6 electron domains around the central atom, that is the bottom row, that's the octahedral family. And when you have no lone pairs, you just have the basic octahedral shape. Okay, and the octahedral shape, I'm going to take these sets of 90-90 angled bonds. Specifically, I'm referring to the angles between the arms and legs, or what should I call them? The angles between the bonds. Okay, so you can imagine phosphorus being at the center here, and at each of these ends you can imagine a fluorine being there, and yeah, there's your octahedral shape. That's your octahedral shape right there. If you connect each end to each other end, if you connect all the vertices together, then you can probably see how you get that base octahedral shape we saw towards the beginning of the video. The one with the, I guess, bluish diagram, where everything kind of looked triangular and all that. But yeah, so the electron domain geometry is octahedral. I guess I'm just going to abbreviate it. Electronic is octahedral. And the molecular, which I'm also going to abbreviate, is also octahedral. The molecular geometry is also octahedral. Okay, let's look at the next one. I know I want to go back to this, so I think it would be better not to write on top of it, just in case the ink bleeds through. I wouldn't want to ruin this page, so where should I put this? Maybe I should have had another table ready. Oh well, I'll just put it there. I'm not using the keyboard. Okay, next up we have NH3Cl+. Next up we've got NH3Cl+. And maybe this time I'll divide it into 3 spaces. Yeah, because 4 felt a little crowded. So NH3Cl+. No clue what to call that ion. Well, maybe chloroammonium is my guess for what its name could be. But that's just my guess. Anyway, so central atom. You've got nitrogen and chlorine are equally rare. Chlorine has a valence of 1 while nitrogen has a valence of 3. So nitrogen wins out. Nitrogen is the better choice for the central atom. So let's see. 3 hydrogens. They don't need octets. And a chlorine. Give that an octet. And bracket. I remembered it this time. And plus. Oh, wait. I don't even know if we're done yet. Tally up electrons. So 5 from nitrogen. Plus 1 each from the hydrogens, so 3 times 1, plus 7 from chlorine, and then take away an electron to get a positive 1 charge. So 5 plus 3 is 8. 8 plus 7 is 15. 15 minus 1 is 14. Do we have 14 electrons here? I've got 8, 10, 12, 14, all used. Okay, then yeah, we are done. No leftovers to dump on the central atom, and the central atom has an octet, so no need to double or triple bond. Okie dokie. So then, figuring out the number of electron domains, how many bonds or lone pairs do we have around the nitrogen? We've got 4. All of them are bonds, and all of them are single bonds in this case. In fact, I think the first example was the only one where we've seen anything beyond a single bond so far. But even if it's a double bond or a triple bond, it just counts as one region, one domain. Remember that. Very common mistake that students make is they count triple bonds as 3 domains and double bonds as 2. They're just one domain. Anyway, enough of me rambling. Let's figure out the electron domain geometry. If you have 4 electron domains, the electron domain geometry is tetrahedral. That's the middle row. And we don't have any lone pairs, so the molecular geometry is also tetrahedral. It's just the standard tetrahedral shape. Okay, so electronic and molecular geometry. Electron domain and molecular geometry are both tetrahedral. They both make up the shape of a tetrahedron. Tetrahedral, tetrahedral. Maybe what I should have done was divide the page horizontally rather than vertically. Oh well. So what does that look like? Well, you've already seen the tetrahedron, technically. Back when I had the trigonal pyramidal molecule, the sulfite ion, just remove this lone pair, and there you go. So essentially there's nitrogen, there's hydrogen, there's another hydrogen, and there's a chlorine. Just use your imagination a bit. And yeah, tetrahedron. That's the tetrahedral shape. Okay. Next up, what do I have? Next we've got the azide ion, N3-. Next up is the azide ion, N3-. Okay, so nitrogen, of course, is going to be the central atom because it's the only option, and the other two nitrogens are going to be connected to it at least by a single bond. Okay. Give each of these guys an octet to begin with. Tally up electrons, so 3 nitrogens, that's 3 times 5 valence electrons per nitrogen. The -1 charge tells me I've got 1 more electron on top of that. Okay, so that's 16 electrons total, and I've used them. 8 here and 8 there. But the central nitrogen, if we've got no leftover electrons to dump on it, it's going to need double and/or triple bonds in order to reach an octet, because right now it's only got 4 electrons total surrounding it. So there are actually a couple of options here. You could cross off a lone pair from this nitrogen and put it here and make a double bond, and then cross off a lone pair from the other nitrogen to make 2 double bonds, or you could cross off 2 lone pairs from the same nitrogen and make a triple bond on one side, leaving the other nitrogen alone. We actually have 3 different resonance structures for this molecule. I'm going to go with the more symmetric looking one first. I'll draw all of them, and I'll also point out how they don't matter. So cross out those 2, make a double bond there, cross out those 2, put them there. Okay, now everybody has an octet. The other resonance structures, one looks like this. And one looks like that flipped over, so like this. And you'll notice that no matter which resonance structure you pick, the number of electron domains around the central atom remains the same. No matter which of the 3 resonance structures you pick, the number of domains is still 2 surrounding the central nitrogen. Okay, 2 electron domains. Hopefully you remember this from an earlier example. That's the linear shape, for which there is only 1 molecular geometry. So that's a linear. So electronic geometry is linear, and molecular geometry is also linear. Okay, what do we have next? Next up, we've got phosphorus trifluoride. Next up, we've got phosphorus trifluoride, PF3. Okay, let's see what this is going to look like. Oh, I guess I messed up my color choice. Oh well. It's not like I'm known for color consistency. I swap colors at random pretty much all the time. Well, it's not totally random, but I'm rambling now. PF3. So phosphorus is our central atom. Put 3 bonds to fluorines and give them each octets. All right, tally up electrons. So phosphorus brings in 5. Each of the 3 fluorines brings in 7. No charges that we need to account for. 5 plus 21 is 26. We've used 8, 16, 24 out of 26. So 2 left over, dump them on the phosphorus. This should look familiar. This is basically what we got with the sulfite ion. This is basically the same scenario we had with the sulfite ion. Phosphorus has 4 electron domains surrounding it, and only one of them is a lone pair. One of them is a lone pair. So if we go back to our chart, and by the way, you do have to memorize these shapes. You do have to memorize them. But if you start by memorizing the basic shapes, the electron domain geometries, and then just kind of reason your way through how substituting atoms with lone pairs leads to different shapes, if you can master just kind of visualizing how the shapes change from the basic shape in each family, then it will significantly reduce the amount of memorization. Also, if you try to really understand the meaning of the names, that will help a lot. Rather than just rote memorization, understand that trigonal means something to do with triangles, and planar means something to do with being a flat shape, and stuff like that. The names actually do make sense if you take the time to think about them. Anyway, from the tetrahedral family, that's where we're looking because we had 4 electron domains. And specifically, we had the case where one of those 4 domains is a lone pair. So that's the trigonal pyramidal shape, which we have seen before. I'll put it back up in front of you right now. There's your trigonal pyramidal shape. Again, to see the shape, just kind of ignore the presence of the lone pair and see what shape is left behind after you kind of just cover up the electrons. Treat them as being invisible because electrons are small compared to atoms. Just focus on the shape that the atoms make, and that's a triangular pyramid, or a trigonal pyramidal shape as it's officially called. So yeah, electronic geometry is tetrahedral. Molecular geometry, I guess I'll write it down here. Molecular geometry is trigonal pyramidal. It's a triangular pyramid, not a flat triangle. Trigonal pyramidal. Okay, off to the next one. We have CH3+. CH3+, which in organic chemistry is called the methyl carbocation, but I digress. Oh, wait, don't want to write over this. Almost made a terrible mistake there. I mean, well, is it really? Yeah, it's bleeding through, but it's not too bad. Okay, where was I? CH3+. So let's segment this paper into roughly 3 sections. Yeah, I'll just stick with vertical. And over there, we're going to have CH3 plus. Okay, what's this going to look like? So carbon is our central atom. Let me switch to lime green. And single bond each hydrogen. Hydrogen doesn't need an octet, so we're done with our guest atoms. Tally up electrons. We've used 2 and 2 and 2. We've used 6. And how many do we have? Carbon brings in 4 valence electrons, plus 3 hydrogens, each bringing in 1. And then the positive charge tells us that we're missing 1 electron, so minus 1. So 4 plus 3 is 7, minus 1 is 6. That's the number of electrons we've used. So no leftovers to put on the carbon atom. And carbon has less than an octet, but there's nothing we can do about it. You don't have any lone pairs on any of the hydrogens that you could bring in to make a double bond or a triple bond. So yeah, we're stuck with this shape. Okay, so we've got 3 electron domains around our central atom. For 3 electron domains, that's the trigonal planar family. And we didn't have any lone pairs on our carbon, so it's the basic trigonal planar shape without modifications. All right, so electronic geometry, trigonal planar, which is a fancy way of saying flat triangle. And molecular geometry is also trigonal planar. Trigonal planar. And molecular geometry is also trigonal planar. On to the next one. Oh, I almost forgot. Brackets. And plus. Did I miss any of those brackets in the last page? No, I did not. Okay, that's fortunate. Next one we have is bromine trifluoride. Bromine trifluoride, BRF3. BRF3. Okay, so bromine is going to be our central atom in this case. And we'll connect it to 3 fluorines. Give each fluorine an octet. Tally up electrons. Bromine brings in 7 valence electrons. Fluorine has 7 valence electrons as well, so that's 7 plus 3 fluorines, each bringing in 7. That's 7 plus 21 equals 28. Maybe I should be writing the totals, but I didn't write the totals before. 28 electrons total. How many electrons used? Well, we've used 8, 16, 24. So that leaves 4 leftover electrons. We need to put them on the central atom as lone pairs. So there we go. 4 electrons on bromine. Okay, what shape do we have here? We've got 5 electron domains on our central atom, 3 of which are bonds, 2 of which are lone pairs. So that is the, that's the trigonal bipyramidal family. Electronic geometry is trigonal bipyramidal, second to last row. And when we have 2 lone pairs, we modify the shape so that the molecular geometry comes up as T-shaped. And I realize I haven't been showing you all the other shapes for the recent molecules, have I? I think I did show you PF3. I didn't show you the shape for this one. Okay, so we'll go back to that in a bit, but let's take a look at this. So it's from the trigonal bipyramidal family, so start with the basic trigonal bipyramidal shape that I have here. And you've got two lone pairs on the central atom, so the lone pairs are going to be attached to this triangular middle section of the trigonal bipyramidal shape. That's where they always attach. They never attach on these far ends here or here. They never attach on the axis of this like straight line part of the molecule. They're never going to replace the axial bonds. They'll always replace these bonds that are on the sides, which are called equatorial bonds. You don't really need to know those two words, axial and equatorial, but it might help to know them. Anyway, let's place a lone pair on here. And let's place another lone pair on here. Okay, and if I ignore the presence of the lone pairs, if I cover them up, basically, then what's left is the shape of the letter T, especially if I hold it like that. Can you see it from that angle? Yeah, there we go. Yeah, that's a letter T with, I guess, extra long serifs, but that's why it's called T-shaped. And I guess if you look at it sideways, I guess this also counts as a T, but I've always seen the T shape as referring to this rather than this. But anyway, that's the T shape. So you see, the names make sense. It's not going to be that hard to memorize them if you can make sense of the names. Anyway, there was one that I skipped that I need to go back to, which was the CH3+. That's the trigonal planar shape. There it is, flat triangle. All bond angles are 120 degrees. I'll be talking about bond angles later. But yeah, there you go. That's the flat triangular shape. So imagine a carbon right here in the middle and a hydrogen on each of these ends. Okay, next molecule/ion is the perchlorate ion. Perchlorate. If I'm not mistaken, that's going to end up being tetrahedral. Hold on. Let me see. If it's going to be tetrahedral, then we'll skip it since we've already seen tetrahedral. Let me think here. So it would be chlorine in the center. Yeah, that's going to be a tetrahedral. Let's skip it. Next one then would be xenon difluoride. Xenon difluoride. Wait a minute. Xenon is a noble gas. Aren't the noble gases unreactive? Well, xenon is one of the bigger noble gases. It's further down the periodic table, and because it's further down the periodic table, it's got a bigger size. And what do we know about atoms with bigger size? They have lower ionization energies. So it's easier to remove an electron from xenon than it is to remove an electron from some of the smaller noble gases. So yeah, xenon is just big enough where if you use the right atoms, you could actually get xenon to give up electrons. You could actually take electrons off of xenon, or at least in this case, get xenon to agree to share. And fluorine, being the atom with the most electronegativity, being the atom that's best at pulling on electrons in the tug of war that is covalent bonding, is perfect for getting xenon to at least put up a struggle for its electrons. So yeah, it is possible to make compounds with the noble gas xenon, specifically using fluorine. I don't know if other atoms also work. The only examples I've ever seen are different fluorides of xenon. Anyway, putting that aside, we have xenon is the central atom. And we've got 2 fluorines to connect to it. Okay, so fluorine, give that one an octet, give that other fluorine an octet. That's a total of 16 electrons used. How many electrons are available? Xenon is a noble gas. It already has 8 valence electrons. 2 fluorines, each fluorine brings in 7, so that's 14 plus 8 is 22. We've used 16 out of 22 available electrons. That means we've got 6 leftover electrons. They're going to be dumped onto the central atom in the form of lone pairs, like that. How many electron domains does xenon have surrounding it? That would be 5. We've got 2 bonding domains and 3 lone pair domains, or 3 non-bonding domains, if that's what you prefer to call them. Let me see. So, oh, right, chart. Let's pull up our chart. So if we've got 5 total domains, that's in the trigonal bipyramidal family. And specifically in the case where you have 3 lone pairs on the central atom, you have the linear shape. You've got the linear shape when you put 3 lone pairs on the central atom of a trigonal bipyramidal molecule or ion. Okay, so what does that look like? So start with your classic trigonal bipyramidal shape. There it is. And let me get 3 lone pairs to put on here. So here's 1. Here's 2. Here's 3. This one's going to be the hardest to attach. Okay, there we go. So if you ignore the lone pairs, then essentially what's left of this molecule is just a straight line. Hence the linear shape. I just realized I forgot to write down the geometries for the previous molecule. Great. You remember one thing, you forget another. Anyway, electron domain geometry for xenon difluoride is trigonal bipyramidal. Trigonal, triangular, bi meaning 2, pyramidal, 2 triangular pyramids connected bottom to bottom. The names make sense. That's why they're not as hard to memorize as you think they are. I know I'm starting to sound like a broken record here, but for some people I have to repeat it that many times or else they won't believe it. Molecular geometry is just linear. Okay, and going back to this was electronic geometry was trigonal bipyramidal. Trigonal bipyramidal. And molecular geometry was T-shape. T-shaped shaped like the letter T. All right. What do we have next? We've got BrO2-. Let's move this and replace it with a new sheet. BrO2-. First, let's divide this sheet into 3 sections. Okay. BrO2-. That would be the bromite ion. Okay, what's this going to look like? I think this is going to be a bent shape. If my predictions are correct. If my predictions are correct, this is going to be a bent shape. So oxygen there and oxygen there. Give each one an octet. Tally up electrons. We've used 16. We have 7 for bromine plus 2 times 6 for oxygen. And then the -1 charge means we've got 1 extra electron on top of that. So 7 plus 1 is 8, plus 12, that's 20 electrons, out of which we've used 16. So we've got 4 leftover electrons, which we can dump on there. And since that's an ion, I need to put brackets around it. All right, there we go. So there's the bromite ion. That is a bent shape. I don't think we've seen that shape yet, so let's take a look. 4 electron domains around bromine. 2 bonding, 2 non-bonding. So 4 electron domains, that's the tetrahedral family. When you've got 2 lone pairs, that results in the bent shape. All right, so if I start with my basic tetrahedral shape, there it is, and I replace 2 of these bonds with lone pairs, 1 there and 1 there, then you're left with the bent shape, because if you ignore these electrons, all you're left with is just this boomerang-shaped, V-shaped thing. We just call it bent. It's like, it used to be a straight line, but it got bent into something shaped more like a boomerang. Okay, so there's a bent shape. Incidentally, the water molecule is also going to be this type of bent shape. The water molecule, I guess I can draw it. Water molecule also has that shape where oxygen has 2 lone pairs on it, and then you've got the 2 hydrogens connected to it. So that one is also a bent shape. Water is a pretty common molecule, so I think it's important to know what its shape is going to be. But it wasn't on this original list, and actually, I'm trying to figure out where to go next from here, because I know we haven't gone through all the possible shapes. What have we not gone through yet? Let's see. There's that one. We've gone through all of those. We've gone through all of those. We still haven't seen a couple members of the octahedral family and a specific member of the trigonal planar family. Okay, so let me look through the book, because apparently this example was not listed in the end of chapter problems. let's do the nitrite ion. So next up is nitrite NO2 minus. What is this going to look like? So nitrogen will be our central atom, of course. Oh, forgot to list the geometries here. I imagine most of you don't mind because you're just hearing me and copying things down, but maybe some people are hard at hearing and need to see it written down. Electronic geometry is going to be tetrahedral. My handwriting is off today. And molecular geometry is bent. Okay, now we can go to our next ion, which is nitrite. So central atom is nitrogen. And then connect two oxygens to that. Give each oxygen an octet. Tally up electrons. So you've got 5 valence electrons for nitrogen itself, plus 2 times 6 valence electrons for the oxygens, and then add 1 electron to create a -1 charge. Okay, 5 plus 1 is 6, plus 2 more 6s is 3 times 6 is 18. We've used 16 electrons so far out of 18, so 2 left over. Dump them onto the central atom. Central atom has less than an octet. What do we do? Well, if you have less than an octet, you can take a lone pair from one of the guest atoms and turn it into a double bond, or take 2 lone pairs and make a triple bond, or take a lone pair from there and a lone pair from there and make 2 double bonds, but that would be going overboard because we only need 1 extra bond. So I can either take 2 from here or 2 from here, it doesn't matter. Let's take 2 from there, and that gives you a double bond there. You could also have taken the 2 from that other side, in which case you would have gotten this. So those are 2 different resonance structures, but like we saw in the case of the azide ion, it doesn't matter which resonance structure you pick. All the good resonance structures have the same shape. And let me bracket these and state the charge. Okay, how many electron domains around my nitrogen? I've got 3. 1 bonding domain there, another bonding domain there, and a non-bonding domain up there. 2 bonding, 1 non-bonding. 3 domains total. 3 electron domains goes with the flat triangle family, also known as trigonal planar. And when you have 1 lone pair, you get another type of bent shape. Another type of bent shape. Okay, so here's our flat triangle. Replace one of the bonds with a lone pair. And if you cover up the lone pair, let's see, can you see it well from there? Yeah. If I cover up the lone pair, then you get this crooked / bent shape. I don't think your teacher would mark it right if you called it a crooked shape, so do remember to call it bent. It's shorter and easier to write, so there's extra motivation. But yeah, it's a bent shape, but this time from the trigonal planar family, as opposed to the tetrahedral family. So, electronic geometry, or electron domain geometry, is trigonal planar, and the molecular geometry is bent. All right, let's take a look at, what should I do next? Let's take a look at iodine pentafluoride. Iodine pentafluoride. IF5. So iodine is our central atom. And I'm going to connect, let's see, I guess 5 fluorines to it. So fluorine there, and a fluorine there, and a fluorine there, and a fluorine there, and a fluorine there. Okay. Give each an octet. And there we go, tally up electrons. Iodine is a group 7, well, a group 7A atom, so 7 valence electrons. Fluorine is also in main group 7, so plus 5 times 7. 7 plus 5 times 7 is 6 times 7 is 42. How many electrons have we used? We've used 8, 16, 24, 32, 40. 40 out of 42, so 2 leftover electrons to dump onto iodine. All right, how many electron domains on our central atom? We've got 6 of them. 5 bonds to fluorine atoms and 1 lone pair. So 6 electron domains, that's the octahedral family, bottom row. And let's see, if we have 1 lone pair, that gives us the square pyramidal shape. So let's see how that plays out. Here's our basic octahedral shape, where you've got 1 central atom in the middle connected to 6 other things. And if I replace one of those 6 things with a lone pair, and I cover up the lone pair, I hide it, then maybe you can see how this would make a square pyramid if I connect this top point to each of these points separately. Imagine connecting them, and you can see those are basically like the skeleton of a pyramid. They're the underlying structure of a regular square pyramid. So hence the name square pyramidal for the molecular geometry. Okay, so electron domain geometry is octahedral. Octahedral. And the molecular geometry is square pyramidal. Just a regular traditional square pyramid like the ones in Egypt. Okay, and I think there's one more common shape that we haven't covered. 3 that haven't been covered overall if you consider the whole chart, but I did mention that 2 of those are uncommon, so I'm not going to cover them. Let me see if I can find us an example of, I think I found it, xenon tetrafluoride. And I guess those who've been paying attention and keeping track can already guess what the next shape is going to be just by process of elimination, but I would hope that you follow along and try to figure it out, you know, the more traditional way. So next up we've got xenon tetrafluoride. I suspect is going to give us the desired shape. Xenon tetrafluoride. So that's going to have xenon as the central atom, and I'm going to do that. So 4 fluorines attached to it like that. And if my hunch is correct, we're going to have 2 lone pairs on the xenon. Let's check. So xenon brings in 8 valence electrons, plus 4 times fluorine brings in 7. So 8 plus 28 is 36. We have used 8, 16, and then another 16 there is 32. So we've used 32 out of 36. We've got 4 leftover electrons. Dump them onto the xenon. Xenon has more than an octet. Nothing you can do about that. Okay, so there's xenon tetrafluoride. Xenon has 6 electron domains surrounding it, 2 of which are lone pairs, 4 of which are bonding domains. So that's going to be in the octahedral family. And specifically with 2 lone pairs, it's going to be the square planar shape. It's going to be the square planar shape. Okay, so let's see how that works out. So here's your traditional octahedral base shape for when you've got 6 electron domains. I'll replace one of those with a lone pair here. And then where do I place the other lone pair? I have to place the other lone pair on the exact opposite side, because remember, electrons are like charges, and if they get close to each other, they repel. So ideally, you want to avoid getting them too close to each other if you can. So this is where the next lone pair goes, on the exact opposite side, because all the other places you could put the lone pair is too close to the first one, which messes with things and might create a not so stable molecule or ion. But yeah, so here's what we're left with when we replace 2 of the 6 electron domains with lone pairs. If I ignore the lone pairs and cover them up, then all you're left with, and I guess my fingers are in the way, but if you imagine seeing through that red marker ball, then all that's left is a flat square. You've got an X, and if you connect the ends of that X, you've got a flat square, a square planar shape. Yeah, I wish there was a way to, well, maybe I can cover it up with paper. Papers don't have fingers, unlike my hands. Maybe if I cover it up with a piece of paper, it'll work. I'll cover that side up like so, and does that work? Maybe, kind of, yeah, more or less. Well, I tried. But yeah, imagine those lone pairs as being invisible arms, and all that's left is a bunch of dots you can connect to make a square. A flat square, so square planar shape. Let's see, so electronic geometry, or electron domain geometry, is octahedral. And molecular geometry is square planar. Square, not spare. Square planar. Misspelled that one. Planar. Planar. There. Square planar. Okay, and I think with that we've covered at least one example of each of the common molecular geometries. Some we saw more than once. There is one special molecule I want to mention, which is boron trifluoride. I want to mention boron trifluoride, BF3. So boron trifluoride, if you follow the set of rules that I showed in the previous video and at the beginning of this video for drawing the Lewis structure, then you're gonna get something that's not quite right. You will get the correct geometry, but you won't get the right Lewis structure. So BF3, if you try to draw it using the set of rules that we've been using up to this point, then you'd get this far, you'd tally up your electrons, you'd see boron has 3 valence electrons plus 3 times 7 for fluorine, so that's 3 plus 21 is 24. And then, of course, that's 24 electrons available, and you've used 8, 16, 24 already. So at this point, the next step would be to use lone pairs to make double or triple bonds, since the boron has less than an octet. But this molecule is an exception. Boron is perfectly fine with less than an octet. Boron is fine with 6 electrons around it, what's sometimes called a sextet. A sextet, a set of 6 electrons surrounding the boron atom. So yeah, and of course you can actually make molecules where the boron will have an octet, so it's not like boron hates octets, it's just for some reason able to tolerate less than an octet. But yeah, this would be a classic trigonal planar shape for those wondering. Electronic is trigonal planar, and molecular is also trigonal planar. Trigonal planar, and the molecular is also trigonal planar. Okay, so we've had our fun with these molecules and the models. I would expect you to practice this some more and really get comfortable looking at these 2D Lewis structures and imagining the corresponding 3D shape that goes with them. This is going to be important for the upcoming chapter where we talk about how molecular shape affects some of the physical properties of different substances. It's going to be really, really important to look at the 2D Lewis structure and visualize the 3D model in your head. If you can't do that, there are sorts of mistakes that you're likely to make because of the 2D image being misleading. So yeah, I don't know how many anime fans are out there, but I have some bad news for you. In the world of chemistry, 3D is better than 2D. Those of you who don't know anime are probably not going to get that joke or appreciate it. Anyway, so we're going to go back and revisit these molecules or ions, because there are some extra details that we haven't talked about. There's more theoretical stuff, and it's time to start covering that stuff. Let's see. I've got way too much stuff on this table. Okay, I'll move these here, put them inside the book. I'm going to need them for later. And I guess I'll close this up for now. Okay, I'll put that aside for the time being. All right, so now we need to talk about some more theoretical stuff. Okay, I guess that arrangement was not a good one. Hopefully it won't fall over that time. Great. It's still falling over. Let me just... Yeah, I think that'll do it. Okay, now my book is stably leaning over the leg of my table. Maybe not the best option, but that's what I'm able to do with the limited space I have around me. Let's see. So where do we want to go from here? There are a couple of things that we need to cover about the nature of bonding and how covalent bonding works. All of the molecules and ions we just drew were covalently bonded, and we need to cover some theories on how covalent bonding works. So the first major theory that I want to cover is something called valence bond theory. Valence bond theory. The basic idea is that covalent bonds form when the valence orbitals, the orbitals that carry the valence electrons, when the valence orbitals of two or more atoms interact with each other. Interact with each other. Okay. That's the basic idea of it. That's the gist of it. So let's take the case of the hydrogen molecule. So with the hydrogen molecule, it's just one hydrogen bonded to another hydrogen. Its one electron is inside of its 1s orbital. And then if you take another hydrogen that has one electron inside of its 1s orbital, and you want to form the bond between them, you just let the orbitals basically get close enough to each other such that the electrons are in both orbitals at the same time. So you make the orbitals overlap with each other. So this changes into this, essentially. And there you go. Each hydrogen magically now has 2 electrons that it can count towards itself. So, seems like a simple idea. And of course, the amount of overlap depends on how close that these 2 atoms can actually get to each other before they start repelling each other. Why would they start repelling each other? Well, first let's take a look at this diagram. And you're going to want to read it from right to left. So first you've got 2 hydrogen atoms. You count each of their energies separately and add them, and they have some sort of energy that's approximately 0 to start with. But as you move towards what you see further to the left, as the hydrogens get closer to each other, their energies become more negative. They decrease in energy. Up to a certain point. Beyond a certain point, once you see where you have the bottom of that valley in the graph, if you continue going left from there, in other words, continue bringing the hydrogens closer, you actually end up increasing the energy. You end up making the molecule or potential molecule less stable. If you want something stable, try to give it as little energy as possible, because if it has extra energy, then it can do stuff with that energy, such as breaking apart, for example. So to make stable bonds, you want to minimize energy. Less energy means more stability. But why is it that bringing the hydrogens too close makes it less stable? Well, consider the protons in the nucleus. Consider the protons in the nucleus for each hydrogen atom. If I were to draw two hydrogen atoms, I'll do them in different colors so that we can tell them apart. If I were to draw one hydrogen atom like that, and then draw another hydrogen atom like this, this amount of overlap would allow the nucleus of the first hydrogen, which has a proton in it, to be really close to the nucleus of another hydrogen, which also has a proton in it. And if those protons get too close to each other, they start repelling each other. So if you get closer, but not too close, the electrons of one hydrogen will get closer to the proton of another hydrogen. And that's great. That increases stability because, well, I guess you'd need to know your physics a little bit, but essentially the potential energy between opposite charges decreases as they get closer, while the potential energy between same charges increases as they get closer. So at first, as these two hydrogen atoms are getting closer to each other, they're becoming more stable because, sure, the protons are getting closer to each other, but the electrons are getting even closer to the protons of the other hydrogen, or the proton of the other hydrogen. So that more than makes up for it. But past a certain point, you start getting the protons really close to each other, but also the electrons are getting too close to each other. So the electrons in these shells are also getting too close to each other, and because electrons are like charges, they will have an increase in potential energy as they get closer to each other, just like the protons do. So yeah, you want to get close, but you don't want to get too close. You get too close, the protons increase in potential energy starts to outweigh the decrease in potential energy between those protons and the electrons of the other atom. I know that was all a mouthful, but you don't need to memorize that chart or remember this reasoning. It's really just for the students that are curious and really care about it, which I would hope is everyone, but I digress. But yeah, so that's the basics of valence bond theory. Of course, valence bond theory comes with its problems because it fails to explain some of the shapes that we just saw. Before we get to that, let's talk about the importance of overlapping orbitals and all the different types of overlap that you can have. So, under valence bond theory, we imagine orbitals overlapping each other so that they can share electrons. And there are different ways in which orbitals could overlap. You could have direct overlap, like we see in the figure to the left. They just, overlap directly. They run straight into each other. Or you could have indirect overlap, kind of like what you have in the image on the right. And direct overlap tends to be the strongest and best overlap. The greater the size of the overlap region, the better the bond, the stronger the bond, generally speaking. So that sort of angled overlap, it leads to less overlap overall. You have a smaller space in which both orbitals are in the same place, so it's less beneficial. It's not as strong of a bond if they overlap at an angle like that. I don't think I've ever seen any scenario where bonds would overlap at an angle like that. I think that's just a theoretical drawing. But yeah, the orientation of the overlap matters. If it's head-to-head or direct overlap, it's generally going to lead to stronger bonding. So we say that head-to-head overlap, any overlap that results from head-to-head orbital overlap, we call that a sigma bond. We call that a sigma bond. So direct overlap, let me write it down. Oh, wait, you guys can't see that. Hold on. Here we go. So direct overlap of orbitals that creates what's called a sigma bond. The Greek letter sigma can be written like that. So sigma bond, pronounced sigma. And yeah, going back to that diagram, you see three different examples of direct overlap: an s orbital with an s orbital, an s orbital with a p orbital, and a p orbital with a p orbital is basically what you're seeing in those three drawings. But we also have indirect overlap, not at an angle like what you saw in that previous diagram, not the most recent one, but the one before it. But rather, instead of them overlapping at an angle, you can have orbitals overlapping side to side, like what you see here. So in this figure, you've got two p orbitals that just overlap side to side, and it works. It does happen. It's a thing that happens in a lot of molecules, but it only happens when it has to. If you have the choice between direct overlap and indirect overlap, between head-on versus side-to-side, head-on overlap should be your first choice. Side-to-side is what you do when you have no other options. This creates a, generally speaking, weaker type of bond, which we call a pi bond. So indirect overlap, let me try rewriting that. Indirect overlap, we call that a pi bond. A pi bond. So yeah, generally speaking, pi bonds are weaker than sigma bonds. There might be exceptions to that because this is chemistry after all. And in chemistry, there is almost always an exception to every pattern we establish. It's almost as if there are no rules. Anyway, that's sigma and pi bonds. So we'll revisit the topic of sigma and pi bonds later on and talk about it in some more detail, figure out how many sigma bonds and pi bonds we have in the molecules and ions we drew. But those are a couple of concepts that emerge from valence bond theory. Unfortunately, there is a problem. There is a problem that valence bond theory doesn't really account for, which is not easy to see unless you look at energy diagrams. So if I take a look at a molecule such as methane, CH4, or carbon tetrahydride, if that's what you want to call it. If I look at CH4, so it's going to make a tetrahedral shape. And the problem here is, well, look at the energy diagram for carbon. Carbon, so here's your energy axis. I guess I'll just use a capital E to represent energy. Carbon is, I'm just going to focus on the valence shell, so I'm going to start with 2s. It ends in 2s2, 2p2. Valence bond theory doesn't explain this because under valence bond theory, the idea would be that only the unpaired electrons would have the orbitals containing them overlap with the orbitals of another atom. So under valence bond theory, there's no explanation for why carbon can bond to 4 hydrogens when the energy diagram would suggest that it can only bond with 2. The energy diagram would suggest that carbon take let's say the p orbital along the x-axis and take the p orbital along the y-axis, for example. We'll ignore the p orbital along the z-axis. We would say that each of those orbitals has one unpaired electron. And you would think then that the motivation is for 2 hydrogens to come along. The motivation would be for 2 hydrogens to come along. So a hydrogen here and a hydrogen here. And overlap their 1s orbital with one of the 2 p orbitals of carbon. But we know that CH4 is a real molecule. This happens. So what's going on? How do we get 4 unpaired electrons when 2 of them are already paired? The other problem is, even if you were somehow able to force carbon to make 4 bonds, if you were able to unpair these electrons, maybe you could excite this electron and make it jump up into that empty p orbital there. Even if you were to do that and create 4 singles, that would still leave another problem. And the other problem is that the actual methane molecule, we know all 4 of its bonds are equal. All 4 of its bonds are equivalent to each other. It's not like one bond is shorter than the other 3 or longer than the other 3. So that would suggest then that all of the bonds are the result of the overlap of orbitals that not only have the same size but also the same energy. And the 2s and 2p, while they're both in the second shell and will have approximately the same energy, they'll be close to each other, they are still different in energy. So we would expect to see one of these carbon-hydrogen bonds be different from the other 3, but we don't see that. So what's going on? Introducing hybrid orbital theory. Introducing the concept of hybridization and hybrid orbitals. Hybridization and hybrid orbitals. So here's what was proposed, and the math seems to check out. We can't go over the math because it's complicated, beyond the scope of a general chemistry course for late high school, early college. But yeah, according to the math, apparently, you can do the following with orbitals. You can take a bunch of orbitals, group them together, and replace them with orbitals that have the same total energy. You can take any number of orbitals, mix them, and replace them with new orbitals with different energies. So what happens in methane, essentially, is, let me draw a brand new energy diagram for it. Again, I'm going to skip the 1s, just going to focus on the valence shell. So here's your 2s2, here's your 2p2 for carbon. So what carbon does as the central atom is it takes all 4 of these orbitals from its second shell and blends them all together. You just take an s orbital plus 3 p orbitals, blend them together, and you get 4 new orbitals that have an energy that's somewhere between the originals, but their total energy is the same. I'll attach numbers to it so that it'll make more sense. Let's suppose that the 2s orbital has an energy, and I'll just make up a number here. Let's say the 2s orbital has an energy of 9. Let's say the 2s orbital has an energy of 9, and let's say each of the 2p orbitals has an energy of 15. That's consistent with what we said about p orbitals being higher in energy than s orbitals. Okay, so I've got a 9 here, and a 15, and a 15, and a 15. What happens if I add all those together? That would be, let's see, 9 plus, well, 3 15s is 45, plus 9 is 56. Okay, so I've got 56 is the total energy of these 4 orbitals. Then I can replace them with 4 orbitals, any 4 orbitals, as long as they add up to 56 units of energy. Let's divide it evenly by 4. So 56 over 4, that would be 14, right? Yeah, that would be 14. So replace your 2s orbital and all 3 of your 2p orbitals with, let's do this in navy blue, which probably looks like black to you guys. So there's a new energy diagram. So an energy of 14 is going to be pretty close to where the 2p level is. So we've got 4 new orbitals, each with an energy of 14. Each of these orbitals has an energy of 14, and now the 4 electrons can go into each orbital unpaired. So the electrons have the same total energy in the end as they did before. Actually, this is more stable. You actually have less total energy for the electrons than before, because these 2 electrons are paired, and when electrons are paired, that raises their potential energy. So in fact, this is actually more stable than this setup when making molecules, because you do actually end up with a smaller total amount of energy for your electrons, though the base energies of the orbitals add up to the same total as they did before. It's just the benefit of unpairing two of your electrons saves you some energy. Or, well, saving you energy is probably not the right phrase. Just reduces the overall energy. But yeah, now we've got this weird hybrid of an s orbital and 3 p orbitals. And what we would call this, we'll cover it later on. What we call these, we call them sp3 orbitals. Essentially, these orbitals are 1/4 s-like and 3/4 p-like, if that makes any sense. We'll see some visuals later that can help us make sense of what these sp3 orbitals look like. But the main point is now we have a way to get 4 unpaired electrons all with equal amounts of energy, thus explaining why all 4 of carbon's bonds to hydrogen are equivalent to each other, because they're all formed from the overlap of orbitals that are of the same energy. So this bond over here is due to the overlap of an sp3 orbital from carbon and an s orbital from hydrogen. And you can pretty much say the same for those other 3 carbon-hydrogen bonds as well. I'm not going to draw it all out. But yeah, there we go. Hybridization solves a lot of the problems that valence bond theory could not solve on its own. So let's take a look at the different kinds of hybridization that we can do. Because you don't actually have to hybridize all of the orbitals available to you. You don't have to blend all the orbitals, you only need to blend as many as you need. And that can actually make sense because the more high energy orbitals you put into your metaphorical blender, is metaphorical the right word? Our hypothetical blender. The more the more p orbitals you put into that blender, the more high energy orbitals you put into that blender, the higher the energy of the new orbitals you make after you're done blending. So if I just mixed one of the s orbitals with one of the p orbitals, that would be a 9 plus 15 is 24. Split that into 2 new orbitals, you'd get 2 orbitals with an energy of 12 each, instead of 4 orbitals each with an energy of 14. If you don't want to make 4 bonds, if you only plan on making 2 bonds, then maybe that would be a better idea. 12 is less than 14. Of course, don't take my numbers too seriously. I just made them up to illustrate the idea. In fact, if I was being realistic, these numbers should be negative. This would be like negative something, and this would be even more negative, right? Because higher energy is less negative. But I digress. Let's take a look at what happens when you mix one s orbital with just one p orbital. Okay, there's a visual there for you. So you start with an s orbital and a p orbital, both presumably from the same shell. They blend together, they hybridize, and the result is those 2 weird yellow orbitals that you see in the top right corner. So one of them faces to the right, the other one faces to the left, and they kind of look like p orbitals, but they're lopsided. One side is more inflated than the other, so you could say these orbitals are 50% s, 50% p, and that shape is the result of that. So those are called sp orbitals because the s and p that were blended to make them were mixed in a 1-to-1 ratio. So yeah, if you take those 2 yellow lopsided orbitals and look at them together in the same atom, then you would essentially see an atom that has two big lobes, one on each side. And as for the little lobes, where did they disappear to? We removed them from the drawing for convenience so that the drawing doesn't look too crowded. But they're still there. We just focus on the major lobes instead of the minor lobes. So that's sp hybridization. And of course, we can see what that looks like in terms of energy diagrams. So if I pull up this energy diagram for you, here's a beryllium atom, and let's say this beryllium atom wanted to bond with two chlorine atoms. No need to hybridize all four of your orbitals, just two of them will do since you're bonding to two atoms. So you hybridize one of your 2s orbitals with one of your, well, your only 2s orbital with one of your p orbitals, and you get a pair of sp orbitals. And you're left with a pair of 2p orbitals that are still untouched. Remember that for later. Those untouched p orbitals will come into play for some molecules. They also have a purpose to serve on occasion. So don't forget about those. If you don't use all your p orbitals for hybridizing, then you will have some left over and you might end up doing other stuff with them. But yeah, that's sp hybridization when you mix one s with one p. Okay, let's take a look at sp2 hybridization. Can you guess what this is going to be? You mix one s orbital with two p orbitals. So let's say the one along the x-axis, and I guess they also took the one that points along the y-axis for this example. You mix all three, and you end up with three equivalent orbitals. 3 orbitals in, 3 orbitals out. That's basically the rule. The number of orbitals you put in equals the number of orbitals you get out after blending. So we get 3 orbitals that are equivalent to each other. They're equally spaced out from one another, and because they're equally spaced out from one another, you see in that final picture in the bottom right corner that when you draw all 3 of them in the same drawing, they're spaced out in a flat triangular shape. I wonder if it's connected to the trigonal planar family in any way. Okay, so let's look at this in terms of energy diagrams and get a move on. So yeah, suppose you've got, I guess their example here is a boron atom, and suppose it wants to bond with 3 hydrogen atoms. If you want to make 3 bonds, you don't need to hybridize with all 4 orbitals. You can just use 3. So go for cheap. An s orbital with a pair of p orbitals. Leave one of your p orbitals untouched, and you get a set of 3 sp2 orbitals, as we saw in the previous figure. And I guess I could do a calculation based off the numbers I made up. So if we continue with treating s orbitals as having an energy of 9 and p orbitals as having an energy of 15, an s with 2 p's would be 9 and 15 and 15, so that's 39 spread out over 3 orbitals, so your 3 new orbitals would each have an energy of 13. Okay, yeah, I think I'm glad I put numbers to those orbital energies now, because I think it's making it easier to grasp that we are making lower energy orbitals. Yeah, instead of what did we have before? We had 2 electrons in the s, so that's 9 and 9, and 1 electron in the p, so that's 15 based on the numbers I made up. So that's 18 plus 15 is 33, but you have to take into account that it's actually more than 33 because the two s electrons are paired. So let's assume the extra energy from having the electrons paired actually makes it so that the total energy is more than 39. Then the new sp2 orbitals giving the electrons a total energy of 39 is going to lead to something more stable overall, since the total energy would be less. But I guess that would mean that pairing the electrons would add more than 6 units of energy. I don't feel comfortable with 6 being the amount of energy added due to pairing, especially then, since that's 2/3 of the energy I've set for my s orbital. But that's what happens when you make up your own numbers. I'm sure it checks out when you do the math with the actual numbers. But I'm rambling again. Let's get a move on. Let's take a look at sp3 orbitals. We already talked about them, but let's take a look at their shape. So this is where you mix all of your valence orbitals. All of your valence orbitals if you're in the second shell. In the third shell, you might also be mixing d orbitals. But at least for s and p subshells, if you hybridize all 4, then you get 4 different sp3 orbitals, each one pointing in such a way that it's pointing as far away from the other 3 as possible. And once you put them all together, they make up this shape that you see in the bottom right, which seems awfully familiar. That looks kind of tetrahedral. I wonder if this is related to the tetrahedral family of molecular shapes. And yeah, here's an energy diagram, not too different from what I showed you. In fact, it's exactly what I showed you because their example is the methane molecule CH4. So yeah, there's that. Let me see. And then for these 2 other types of hybridization, they don't really show you what all the orbitals look like pre-blending, but you can also go past mixing s orbitals with p orbitals. You can also blend in some d orbitals. So if you take an s orbital and 3 p orbitals and 1 d orbital, so that's 5 atomic orbitals total, and you blend them together, you make 5 sp3d orbitals, 5 hybrid orbitals. And yeah, when you stack all 5 of those orbitals together on the same atom and draw them all in the same picture, then you get that shape that you see over there, which resembles the trigonal bipyramidal shape. Okay, I think you guys get it. I think you've had enough of my hmming. One more to go. If you take 2 of the d orbitals and blend them in with your s orbital and all 3 of your p orbitals, you get this. So let's see, we mixed an s and 3 p's and 2 d's. That's a total of 6 orbitals. You blend them and you get 6 hybrid orbitals of the sp3d2 type. So they're 50% p, 33% d, and about 17% s is how I would describe them. That's the ratio in which those orbitals were mixed. And you might be wondering, well, what about hybridizing with more d orbitals? After all, you have 5. Well, I've never encountered any examples where you have to go past that point, because at that point you're kind of connecting way too many atoms to your central atom, And I don't know if there are actually some real-life examples where you go beyond sp3d2, but in theory it should be possible to go beyond sp3d2. I can at least say that. There's no reason mathematically why it's impossible, but I think the reason that we don't talk about anything past sp3d2 is because either it's too messy or we don't have enough real-life examples, if any, to justify studying those, especially in a general chemistry course. Maybe in a more advanced chemistry course you might learn about that stuff if it's actually worth studying according to chemists. I don't know much about it. So that's all I can say on going past sp3d2. Okay, so where do I want to go from here? Well, I'd like to revisit all of the molecules and ions we just covered, all the molecules and ions we just drew, and I want to figure out what the hybridization is for their central atoms. So, in case my heavy-handed hinting and hmming didn't clue you in, yeah, the hybridization is very, very closely connected. The hybridization of a central atom is very closely connected to the electron domain geometry of a molecule or polyatomic ion. They're very closely connected. The number of electron domains surrounding the central atom is going to determine what the hybridization is. The number of electron domains surrounding the central atom is the number of hybrid orbitals you have to make. So in this case, I've got 2 electron domains, a single bond and a triple bond. So I would need to blend 2 orbitals, use the lowest energy orbitals you have. We have an s, we only have one of those, so we use it. Next lowest in energy is the p subshell, so we grab one of our p orbitals, mix one s with one p. The HCN molecule, specifically the carbon in HCN, is sp hybridized. The carbon is sp hybridized. We can actually determine the hybridization of the other atoms in the molecule, not just the central atom. Usually it's the central atom we're concerned with because that determines the overall shape of the molecule. But yeah, this nitrogen is also hybridized. Hydrogen is not because, well, hydrogen can't hybridize. It's got 1 electron in its first shell, which only contains the s subshell. There's a 1s, there isn't a 1p, so hydrogen can't hybridize. Hydrogen is just using a regular s orbital. Nitrogen has 2 electron domains, a triple bond and a lone pair. So nitrogen is going to require 2 hybrid orbitals, mix 1s with 1p. Nitrogen here is also sp hybridized. So yeah, you can definitely determine the hybridizations of the guest atoms, as I've been calling them. But typically the focus is on the hybridization of the central atoms, so that's what I'm going to prioritize. Maybe I'll do the guest atoms for a couple of them, just so we can, broaden our horizons and get a clearer picture of how the molecule really works. But it's not something that most teachers emphasize, so don't worry too much about it. Let's take a look at the sulfite ion. So sulfite has 4 electron domains surrounding it. So that would require 4 hybrid orbitals. To make 4 hybrid orbitals, you need to blend 4 atomic orbitals. 1 s and 3 p's. That gives us sp3 orbitals. Each of these electron domains carries electrons in an sp3 orbital. So you have an sp3 orbital carrying a lone pair. You have an sp3 orbital overlapping with whatever orbital you have from the oxygen to make a bonding pair here, and another one there, and another one there. So let's actually figure out the hybridization of each of these oxygens. So oxygen has 3 lone pairs and 1 bonding pair. That's 4 electron domains. 4 electron domains is 4 orbitals blended to make 4 hybrids, so that's sp3 again. So the oxygens are also sp3 hybridized in this case. The sp3 orbital of an oxygen overlaps with the sp3 orbital of a sulfur so that they can pair up their electrons. And of course, the other sp3 orbitals of oxygen are just holding on to those lone pairs. Okay, sulfur, 5 electron domains, sulfur tetrafluoride to be specific, 5 electron domains, 4 bonding, 1 non-bonding. So 5 domains requires 5 orbitals, or 5 hybrid orbitals to be specific, which require 5 molecular orbitals, an s, and 3 p's, that's 4, and then 1 d, that's 5. sp3d. Okay, anything in the octahedral family has 6 electron domains, so that's going to require 6 orbitals, an s, all 3 of your p's, and 2 of your d's. That gives you 6 orbitals blended to make 6 hybrid orbitals, which will give you the octahedral shape. Okay, moving on to the next one. We had this NH3Cl plus ion. So nitrogen has 4 electron domains around it. That requires 4 orbitals. That's going to be sp3 hybridization. All right, let's look at azide. The azide ion, if you look at the central nitrogen, it's got 2 electron domains surrounding it. 2 domains requires 2 hybrid orbitals, which require 2 atomic orbitals, 1 s and 1 p. And if I didn't mention it earlier, when I say atomic orbitals, I'm referring to the orbitals before hybridizing them, before you blend them. So yeah, that's sp hybridized. PF3, we've got 4 electron domains, a lone pair and 3 bonds on the phosphorus. So that's going to require 4 hybrid orbitals, which require 4 atomic orbitals, an s and 3 p's. Okay, let's look at another. So next up we had this page. Let's see. This carbon has 3 electron domains around it, all of which are bonding domains. This is going to be sp2 hybridized. 1 s, 2 p's, blend them together, you make 3 sp2s. Okay, the bromine here, we've got 2 lone pairs and 3 bonding regions. So that's a total of 5 electron domains. 5 electron domains, so that's 1 s, 3 p's, and 1 d. That's a total of 5 atomic orbitals blended. Okay, xenon would be, well, that's also got a total of 5, so that's sp3d as well. You've got 3 lone pairs and 2 bonding domains. So yeah, even though these 2 molecules have different molecular geometries, the electron domain geometry is the same, and that's what's connected to the hybridization. In case you haven't picked up on it just yet, linear is SP always. The linear family is always SP. The trigonal planar family is always SP2. The tetrahedral is always SP3. The trigonal bipyramidal family is always SP3D. And the octahedral is always SP3D2. Anyway, carrying on with these, so that's from the tetrahedral family, that's SP3 for the central atom. Can't say that that necessarily carries over to the other atoms. You'd have to look at them individually, but for the central atom, the electron domain geometry determines its hybridization. Or I guess really it's the other way around. The hybridization determines the electron domain geometry. Anyway, nitrite, so that's going to be 1, 2, 3. Well, trigonal planar family is always SP hybridization for the central atom. IF5, that's 6 electron domains, that's octahedral for the electronic geometry, so that's SP3D2 is the hybridization on the iodine. On the fluorines, each fluorine is surrounded by 3 lone pairs and 1 bonding domain. So that's 4 total. I would expect the fluorine to be in a tetrahedral arrangement. So SP3 hybridized. But again, you don't need to worry too much about these guest atoms. I don't think I've ever seen somebody ask about the hybridization of any atoms other than the central atom, except maybe if you're in college, maybe if you have one of those tougher professors, they might ask you for that, but it's not too hard to figure out. I think this is the last sheet. Yes. These were the last 2 we did, so let's have a look. We have, this is from the octahedral family. Due to having 6 electron domains, so SP3D2 would give you the 6 orbitals needed to make the hybrids that arrange themselves naturally into the octahedral shape. BF3, that's gonna be trigonal planar family, so that's SP hybridization for the boron. Or no, SP2, my bad. SP2. Right, 3 domains, 3 orbitals, 1 s and 2 p's. Blend them together and turn them into 3 new SP2 orbitals. Okay. So that covers the basics of hybridization and how to determine the hybridization of the central atom of a molecule or polyatomic ion. But something we still haven't talked about is what happens with leftover p orbitals. We haven't talked about what happens with leftover p orbitals that aren't hybridized when you do sp or sp2 hybridization. Let's go back to our first example, actually. The carbon is sp hybridized. That means you took one of its s orbitals and one of its p orbitals, you blended them together to make hybrid orbitals, but you also have a pair of unused p orbitals. What happens with those? What happens with the unused p orbitals? So let me draw an energy diagram here. Here's your energy. Let's say we've already done our hybridization and we have some sp orbitals here. And here we still have the two p orbitals that weren't used for hybridization. Carbon has 4 electrons, so after hybridization, I would imagine those electrons would be set up like this. Maybe I shouldn't have drawn it so close to the top, but yeah, there we go. I'll have it cross through the bar. I think in some energy diagrams they actually do that. They draw the arrows crossing through the bars, which I guess works to save space. Maybe I should start doing that. But I digress. What was I going to say? Lost my train of thought. Oh, right. So these two orbitals, the sp orbitals, they're just going to do the direct overlap. This sp orbital will overlap with the s orbital of the hydrogen, and then this sp orbital will overlap with, I guess, another sp orbital of the nitrogen. It'll overlap with one of the sp orbitals of the nitrogen. As for these two remaining p orbitals, well, it turns out that nitrogen's energy diagram is also kind of similar. Nitrogen's energy diagram is going to look very similar to carbon's energy diagram here. It's also sp hybridized. It just has one more electron than carbon. So you've got your p orbitals there and your sp hybrid orbitals there. So nitrogen is going to have three electrons in its sp level and 2 unpaired electrons in its unused p orbitals. And so the one electron here, this electron here, is in the sp orbital that overlaps with the carbon's sp orbital directly. As for these two p orbitals, these two p orbitals are going to form the double and triple bond. So these p orbitals are going to overlap with each other, and then I guess I'll use a different color. This p orbital is going to overlap with this p orbital over in the carbon. But the only way they can overlap is side to side. The only way those p orbitals that are left over can overlap is side to side. They don't have the option of direct overlap. Why? Well, because the p orbitals, they start out as a set of 3 orbitals that are all perpendicular to each other. So if one of them, let's take my octahedral model actually, because I guess you can think of this as looking like 3 p orbitals. Imagine your p orbital along the x-axis and the y-axis and the z-axis. So you've got 3 p orbitals that are all perpendicular to each other. If one of these p orbitals tries to overlap directly with some other orbital of another molecule, then these other two, they can't bend over and overlap directly with anything else from that other, did I say molecule? Atom. Maybe this figure will illustrate that a little bit better. So here we've got, is that sp2 or sp? I guess that's the sp2. Oh. We'll work with it. So in the diagram you see in front of you, or figure, yeah, it's not a diagram. Well, it's a figure and a diagram. In the figure you see in front of you, specifically I want to call your attention to what you see in the bottom. You have your 3 hybrid orbitals, which were made by taking an s and 2 of the p's, and you see in the figure to the left two of those sp orbitals overlapping each other directly. They're doing direct overlap, which we referred to earlier as a sigma bond. Meanwhile, you've got the untouched p orbitals of those two atoms. It looks like, yeah, they're both carbon atoms in this case. Those are shown in red and blue. And those guys, they can't bend sideways or tilt themselves in order to reach the orbitals of the neighboring atom. Their only option is to overlap side to side. And as for how they overlap side to side when they're so far away from each other, well, these figures are drawn in a way that makes it easy for us to, show everything. And if we drew them to scale, the p orbitals would actually be bigger, and they'd already be overlapping side to side. We just draw them smaller in our figures for, I guess, ease of communication and for the sake of being able to show everything rather than, having big orbitals block off half of the picture. But yeah, for the realistic molecules, the p orbitals are big enough that they do overlap without really needing to, bend towards each other. You can't really make the orbitals bend. I guess there is a little bit of slight smearing. Maybe that does happen, like what you're seeing in the figure to the right, where it's like the red and blue lobes of that p orbital stretch themselves thin so they can reach each other. I don't think that's what actually happens, because I'm pretty sure, if I remember correctly, it's just the scale of the drawing requires us to do it this way. The size of the p orbitals realistically should allow them to overlap side to side just fine without the need for that smudging that they show in that picture on the right. But yeah, there you go. That's the formation of a pi bond on top of a sigma bond. So the sigma bond forms first because it's more stable. Why would you do sideways overlap if you had the option to overlap directly? So the sigma bond forms first, and then, if need be, a pi bond can form on top of that due to forced sideways overlap. So with the sp2 hybridized atoms, you can form one pi bond because you have one p orbital that can overlap with presumably one p orbital in a neighboring atom. You'd have to have two atoms that have available p orbitals in order to make the pi bond. Okay, what about triple bonding? For triple bonding, you just need to make two pi bonds, which works if you have two available p orbitals that weren't used in hybridization. This is possible if you have something that's sp hybridized. So here we go. We've got, I guess they've shown us in the top, you've got the two sp orbitals, one to the left and one to the right, both in yellow. And then you've got two unused p orbitals. One is, I guess, red-blue going up and down, and the other one is the red-blue going, I guess, in and out of the page, is how I'd describe it. And yeah, if you put this atom, whatever it is, next to another atom that also has two unpaired p orbitals, then you can get two sets of p orbitals to overlap side to side, and you see the result in the two drawings in the bottom. I think it's pretty self-explanatory, but essentially it's a sigma bond from the overlap of a pair of sp orbitals in yellow, and then on top of that, two pi bonds. That's what comprises a triple bond, basically. So yeah, 1 sigma bond plus 1 pi bond, that makes a double bond. 1 sigma bond plus 2 pi bonds, that makes a triple bond. And anything beyond a triple doesn't exist as far as I'm aware. I've never heard of a quadruple bond, so I don't think it exists. But if it did, it would probably be 1 sigma bond and 3 pi bonds. You would need a third leftover p orbital, which I guess isn't possible because you have to hybridize at least one, so you can't have more than 2 p orbitals left. So yeah, it looks like you can't go past a triple bond. And yeah, anything that's not a double or anything that's not a double or a triple bond is going to be just direct overlap, so it's going to be a sigma bond. But yeah, so that's pretty much it for sigma and pi bonds. So let's go back and examine the molecules that we've drawn and count the total number of sigma and pi bonds in each of them. Let's have a look. So, did I say atoms or molecules? Molecules. The molecules and polyatomic ions. Let's look at the total number of sigmas and pi's in each of these. So for hydrocyanic acid, what do we have? We've got a single bond here, so that's 1 sigma bond. And over here we've got a triple bond, so that's going to be 1 sigma bond. And then the other 2 bonds are pi bonds. So 1 sigma between carbon and hydrogen and another one between carbon and nitrogen, so that's 2 sigma bonds. And 2 pi bonds over here to make the triple bond, so that's 2 sigmas and 2 pi's. Okay, what about the sulfite ion? I've got 3 single bonds, so that's going to be 3 direct overlaps, 3 sigma bonds. Okay, over here, sulfur tetrafluoride, 4 single bonds, 4 direct overlaps, so those are 4 sigma bonds. Over here, we've got 6 sigma bonds. All of them are single bonds. And yeah, you don't really have to overthink it. Just every single bond is a sigma bond, every double bond is 1 sigma plus 1 pi, and every triple bond is 1 sigma plus 2 pi's. So we've got 4 sigmas there. We have, no matter which one you look at, here you've got a sigma and a pi and a sigma and a pi, so 2 sigmas and 2 pi's. Here you've got 1 sigma, here you've got a sigma and 2 pi's, so the total is still 2 sigmas and 2 pi's. It doesn't matter which resonance structure you look at. Okay, for PF3, phosphorus trifluoride, 3 single bonds, that's easy, that's just 3 sigmas. Okay, look at the next one. That's 3 sigmas. BRF3, that's also 3 sigmas, just 3 single bonds. 2 single bonds there, so that's 2 sigmas. All right. The bromite ion, 2 sigmas. The nitrite ion, no matter which structure you look at, a sigma here and a sigma plus a pi there, so in total 2 sigmas and 1 pi and 1 pi bond. 2 direct overlaps and 1 indirect overlap. Iodine pentafluoride, so that's 5 single bonds. All single bonds are direct overlaps, so 5 sigmas. And the last sheet, we have, let's see, xenon tetrafluoride's got 4 single bonds, so that's 4 direct overlaps, 4 sigmas. And here we've got 3 sigmas. And yeah, it shouldn't be too hard to figure out. I think this is probably the easiest thing in the whole chapter, is counting the number of sigma bonds and pi bonds. Even if you don't remember how pi bonds and sigma bonds work, if you just remember that singles are 1 sigma, doubles are a sigma and a pi, and triples are a sigma and 2 pi's, counting them is a pretty easy task. So, pi bonds are a result of indirect overlap, and we said earlier that indirect overlap generally leads to weaker bonds. So something that you might have noticed and had questions about in the previous video. Let me see, do I have the diagram for it? Oh, it's probably under... Okay, found it. So, a question that arises, if you remember this chart that we looked at a while back, well, I mean, it's not a while back, it was in the previous video. We saw this chart, and if you look at carbon, if you look at the bond energy for the carbon-carbon single bond, the carbon-carbon double, and the carbon-carbon triple, they're right there towards the top left of the diagram. You notice that the carbon-carbon double bond has an energy of 611, while the carbon-carbon single has an energy of 345. So you notice that the carbon-carbon double does not have twice the energy of the carbon-carbon single. Wait, are those numbers right? Let me double check with my book. Yeah, they're fairly accurate. Okay, we'll go with them. So yeah, you notice that carbon-carbon double is not 2 times the energy of the carbon-carbon single. 345 times 2 would be 690, and you see that the total energy of the carbon-carbon double bond is less than that. It takes less energy to break a carbon-carbon double bond than it does to break 2 carbon-carbon single bonds. And the reason for this is because the carbon-carbon double bond is 1 sigma bond, which has the same energy as the carbon-carbon single, plus a pi bond, which has less energy. So if some of you noticed that in the previous video and were curious about it, there's your answer. Look at the carbon-carbon triple bond. It is not 3 times the carbon-carbon single. If I did 3 times carbon-carbon single, that would be 3 times 345 is 900. Let's just multiply it out in the calculator to save time. 1035. If a carbon-carbon triple had the strength of 3 carbon-carbon singles, its bond energy would be 1035, and clearly that chart shows you a smaller number than that. So again, this is because the extra bonds that you add, moving from a single to a double or a triple, those additional bonds are pi bonds, which are generally weaker than sigma bonds. Do we have any other examples in this chart that we can point to? Carbon-oxygen seems to show a bit of an exception. The carbon-oxygen single bond is 350. The carbon-oxygen double bond is more than twice that. So already you have an exception to the pattern. Go figure, this is chemistry. There are no rules, only patterns with lots and lots of exceptions. Carbon-oxygen triple is more than 3 times the carbon-oxygen double. Maybe this has to do with the polarity of the carbon-oxygen bond, because there is a significant difference in electronegativity between carbon and oxygen. But that's the most immediate explanation I can come up with. I don't know if there's any additional reasons for why this appears to be an exception to the pattern. If we look at the middle row, we've got the middle column, I should say. There's the oxygen-oxygen single with an energy of 140 and the oxygen-oxygen double with an energy of more than 2 times 140. So there's another exception to the pattern. I'm beginning to doubt if there's even a pattern at all. But if you don't have data tables in front of you, you can reasonably make the argument that an oxygen-oxygen double bond should have less energy than 2 oxygen-oxygen singles. It's not true, but if you get asked about that on an exam where you're not given this data, then your instructor is trying to see whether or not you understand the nature of sigma versus pi bonds, not how well you've memorized the bond energies of different bonds. So yeah, just stick with the general pattern, even if the pattern doesn't really show much consistency. Don't you just love chemistry? Okay, is there anything else I want to comment on before I move on to my next item? Let me see. I'm looking at a couple of problems I have here just to check if we need to cover any of them. And I guess I can put them on screen for you to read if you're curious. I don't know if we're going to do these, but I'm reading through them. Useful solvent. So 25 part A is something I'll save for the next video. We talked about polarity of a bond in the previous video, and in the next video we're going to discuss polarity of a molecule, which is not the same thing. It draws on the same thing. It draws on bond polarity, but there's more to it than that. So that's for next. That's for the next video. And yeah, 25 and 26 are talking about what I like to call big molecules, and we'll talk about them a little bit now, but I don't expect you to know how to draw them until we get to the organic chemistry video, which will probably be the last one in this whole playlist. But yeah, one last thing to talk about when it comes to hybridization and hybrid orbitals, and I guess the molecular geometries that result from them, is the notion of bond angles. So we saw that the hybrid orbitals, when you basically stack them all up onto the same drawing, they end up arranging themselves in shapes that match our five main families of molecular geometries, our five electron domain geometries, to be specific. And there was some curiosity in the scientific community, of course, about why the hybrid orbitals were arranged in the way that they were arranged. And the theory that came out to explain why the orbitals arrange themselves in the ways they do, whether it's sp orbitals arranging themselves in a linear pattern or sp3 arranging themselves in a trigonal planar pattern, and so on and so forth. The explanation they came up with was that those arrangements kept the electrons in the orbitals as far away from each other as possible, which helps to reduce the repulsion between them. Extra repulsion between electrons getting too close to each other is going to result in more potential energy, is going to make your molecules less stable. So bond angles are a result of the angles between the hybrid orbitals, and the hybrid orbitals are oriented in such a way that you minimize electron repulsion in those orbitals. So the abbreviation for this theory is VSEPR. Some people pronounce it VSEPR, but clearly it says VSEPR, so I don't know what those people are talking about, but you can call it whatever you want. VSEPR stands for valence, shell, electron, pair, repulsion. VSEPR theory is valence shell electron pair repulsion theory. The idea that hybrid orbitals in a molecule arrange themselves so as to minimize the repulsion between electrons, keep the electrons as far away from each other as possible. So you get a bunch of different bond angles. They depend on, well, first and foremost, they depend on the electronic geometry. They depend on the hybrid orbitals that you're using. So in the tetrahedral shape, for example, sp3 hybridization leads to bond angles of 109.5 degrees. 109.5 degrees apparently is what keeps each of these four ends as far away from each other as possible. But if you introduce lone pairs, if you have molecules that are based on the tetrahedral shape, for example, and you introduce a lone pair, well, that lone pair is going to be closer to the central atom, which brings it closer to the electrons over here. And because this lone pair of electrons is closer to the electrons in here, the electrons over here are going to get repelled away from the lone pair. The electrons in these bonds and the orbitals that are overlapping to make those bonds are going to get repelled away from this lone pair. So in fact, what you'll see is essentially these bonds get pushed. Let me see if I can slightly bend this without breaking it. The bonds get pushed. Why am I struggling with this? The bonds get pushed down like this, which forces them to get a little bit closer to each other. So when you have lone pairs, the bond angles are often less than what they normally would be when you have no lone pairs whatsoever. So that's something to take into consideration. Depending on your teacher slash professor slash instructor, you may or may not need to memorize some of those bond angles after lone pairs are introduced, but let's just list them off for each of the different geometries. So I guess I'll do this on a new sheet. For the linear family, so you've got a central atom and then 2 electron domains around it. The angles between the bonds are 180 degrees. And swapping out one of those bonds with a lone pair doesn't change anything. So an example where you'd swap it out with a lone pair, I guess, would be carbon monoxide. Yeah, carbon monoxide would look like that. So you could say carbon is the central atom here. It's got 2 electron domains, 1 lone pair, and 1 triple bond. So bond angle is still 180 degrees. Replacing this bond with a lone pair doesn't affect that because there's only one way to connect 2 atoms, and it's in a straight line. If it's a diatomic molecule, then it's linear by default. But yeah, so that's the linear geometry. That's the SP hybridization. What about SP2? SP2 is the trigonal planar geometry. And of course its other family members. And typically the bond angles here are 120 degrees each. Typically you have each of these angles being 120 for a total of 360. But in the bent shape, if you replace one of these bonds with a lone pair, then that lone pair repels both of these bonds a little further downward, pushing them closer together. So you're going to get an angle that's slightly less than 120 degrees. Less than 120 degrees. Some people say it's going to be 118 degrees typically, or 117, but just knowing that it's less than 120 is good enough. SP3, the tetrahedral shape. Not sure how I'm going to draw this in 3D, but yeah, imagine this bond essentially sticking out of the page. But that's the SP3. So for SP3, bond angles are typically 109.5 degrees. Typically 109.5 degrees. But if you replace one of these bonds with a lone pair to get a trigonal pyramidal shape, that lone pair pushes these down to a smaller angle. Usually it comes out to about 107.3 degrees, give or take. So the example that they usually give for this is the ammonia molecule. And if you replace two of the bonds with lone pairs, so you get a bent shape like water, if you replace two of the bonds with lone pairs and get a bent shape, then that's two lone pairs. That's more repulsion pushing down on the electrons in these bonds, bringing them even closer together. You get angles around 104.5 degrees, and I think that's specifically in the case of the water molecule. But again, depending on your teacher, you may not have to memorize these numbers. You might just need to remember that it's less than 109.5 for this case, and then even less than 109.5 for the case of two lone pairs. SP3D. I think for this one it might be better to just look at the model. So you've got two different sets of bond angles to consider. You've got the angles between the three equatorial bonds. Those would be 120 degrees each. If you look at it this way, it's basically the same as the trigonal planar when you're just looking down the axis of the molecule. And the other bond angles you need to consider are the angles between an axial bond and an equatorial bond, and those are 90 degrees. Right? You can clearly tell it's a 90-degree angle there. So 90 degrees between here and here, and 120 degrees between here and here. So two sets of different bond angles for the trigonal bipyramidal family. Of course, if you start replacing with lone pairs, if I put a lone pair here, one lone pair will bring these bonds further down and bring them closer together. And because these bonds get brought closer down together, their angle with the remaining equatorial bonds will be less than 90 degrees. So if this thing pushes this a little to the right like that, then you're going to get an angle of less than 90 degrees there. Also, this lone pair pushes down on these equatorial bonds, bringing them closer together, so their angle is going to be less than the default 120 degrees. Okay, and then for the case of two lone pairs, we're going to add here. And I know I stated this before, but for the trigonal bipyramidal shape, you add lone pairs on the equatorial bonds, not on the axial bonds. As for the reason why, well, think about the first one. If I add this lone pair here, then the bonds that are going to be most repelled by this lone pair are just these two bonds over here. These other two bonds will also be repelled by it, but they're further away, so they won't feel the impact as much. So for the most part, it's just two out of the four remaining bonds that are most affected by the repulsion of the lone pair if you place it over here. On the other hand, if you place it up here, then the problem with this is that this is equally close to 3 out of the 4 remaining bonds. That's more bonds feeling most of the impact of this lone pair. That's more repulsion. And of course, if you want to pick what's most energetically favorable, you want to minimize repulsion. So that's why the first lone pair gets placed there. And when the first lone pair is placed there, that kind of limits your options for the next lone pair, because if you place it here, then, well, that's about 90 degrees of separation between those lone pairs. Those are awfully close to each other, whereas if you put it here, they're much further apart. That's 120 degrees apart. So that's the logic behind why you put your lone pairs on the equatorial bonds and not the axial bonds of the trigonal bipyramidal shape. Let's see. So yeah, in this case, so this is of course our good old T-shape. In this case, we say that the bond angles are about 90 degrees. Remember, the lone pairs aren't bonds, so they don't really count. So bond angles for the remaining atoms are 90 degrees. They'll be less than 90 degrees because you've got two lone pairs essentially pushing down on these bonds. So angle will be less than 90 degrees, but still approximately 90. Close to 90, but not quite. However, if we add a third lone pair in the trigonal bipyramidal family, and of course you have to put it here because that's where it's farthest away from the two lone pairs you already have. If I add a third lone pair, suddenly you just have a clean 180 degree angle, because due to the symmetry, each of these electron pairs are equally repelling in every direction, so the total repulsion of the two bonds that remain is 0. The total repulsion of the remaining bonds is 0. There's no net repulsion on the two remaining bonds, so you will indeed just get a straight linear molecule in this specific version of the tetrahedral family. So in this case, electron repulsion due to the three pairs cancels out evenly, all due to the symmetry. Okay, what about our octahedral family? So the basic octahedral shape, all of the angles are 90 degrees. There's 90 degrees between here and here. There's 90 between here and here. Any way you rotate or twist this, the bond angles are 90 degrees. What if I add a lone pair? First lone pair can go anywhere, so I'll put it here. Okay, so this lone pair is mostly going to affect these four bonds, and it's going to repel them, you know, I guess downward the way I'm holding it, and it's going to repel these away, and so you're going to get angles that are a little bit less than 90 degrees. And if I add a second lone pair, where should I add it? Here, it's too close to the first lone pair, and here, and here, and here. All of those are too close to the first lone pair. You want to put it as far away as possible. Goal is to minimize repulsions after all. So that's where it goes. And this way, when they're exactly opposite of each other, when they're at exactly opposite sides of the central atom, their repulsion effects cancel out. And so you get a perfectly flat. You get a perfectly flat square with 90 degree angles again. It's not approximately 90, it's exactly 90 in this case. And yeah, so those are bond angles. Let's go ahead and label the bond angles in all of the molecules we drew. And then we'll reach, I guess, is it the halfway point? Let me see, how long have I been recording? So it's been... Okay, so we're near the, or maybe past the 3-hour mark, if my calculations are correct. I really should start a timer every time I do these recordings. Or use recording software that actually includes a timer. But anyway, let's let's take a look at some bond angles, and then we'll reach, I guess, what might be the end of the video for some of you, depending on whether or not you need to learn what I have lined up next. So let's take a look at our HCN molecule first. Linear shape. What's the bond angle? The angle between those two bonds around the carbon should be 180 degrees. No questions asked. Sulfite ion, bond angles. So this is from the tetrahedral family. For tetrahedral, the bond angles are typically 109.5, but lone pairs tend to shrink that. So less than 109.5 is what you'd want to say here. Less than 109.5 degrees. And again, depending on your instructor, they may ask you to be more specific. They might ask you to say this is 107.3 in the trigonal pyramidal shape. Okay. Next up, we've got sulfur tetrafluoride. So sp3d hybridization, that was the trigonal bipyramidal family. I should just read my notes rather than try to figure it out all over again. But I digress. I've said that way too many times in this one video. I think I've said it more times in this one video than I have in the whole entire playlist up to this point. Where was I? So, right, trigonal bipyramidal, you've got the axial to equatorial angles are 90 degrees, and the equatorial to equatorial bond angles are 120 degrees. The lone pair kind of messes with that, so you get slightly less than 90 degrees and slightly less than 120 degrees. Slightly less than 90 goes to the, what do you call them? The axial to equatorial bonds, and less than 120 between the two remaining equatorial bonds that weren't replaced with a lone pair. For the octahedral shape, this is just the pure octahedral. It's exactly 90 degrees. For all bond angles everywhere. And I guess you could say for the octahedral that you can have 180 degree bond angles if you consider one bond and the bond right across from it, but typically we just consider the bonds that are closest to each other. So in case anybody was wondering about that, you don't go for 180 when 90 is closer. Okay, sp3 tetrahedral, that's 109.5, no lone pairs, so it's going to be almost exactly 109.5. Maybe not the case for this one because you've got hydrogens here and then chlorine here, so there's a little bit of an asymmetry. So yeah, that lack of symmetry might interfere with the angle a little bit. But for the most part, it's going to be nearly 109.5. Azide ion is linear, just 180 degrees. This thing is from the tetrahedral family, less than 109.5 because we do have lone pairs that will bring the bonds closer together by, well, repelling them towards each other. This one is just trigonal planar, and it's going to be a perfect 120 degrees. This one is a T shape, nearly 90 degrees, but not quite. Less than 90 degrees. You've removed 2 of the equatorial bonds, so all that's left is the angle between the one remaining equatorial bond and each of the axial bonds, which is nearly 90 but not quite. Okay, xenon difluoride, that's just a straight line, 180 degrees. Did I say tetrafluoride? Difluoride. That's xenon difluoride. Bromite ion, so that's going to be a bent shape. So less than 109.5 since it's from the tetrahedral family. Less than 109.5, and if your instructor wants you to be more specific about it, for the case of the bent shape in the tetrahedral family, the bond angle is usually around 104.5 if you have an instructor who wants you to be more specific about that. Nitrite. So this is from the trigonal planar family. So bond angles around 120 degrees, but not quite because you do have a lone pair there. A little less than 120. Okay, ion pentafluoride. That's... oh, I guess that's from the octahedral family. I should just look at my notes and not try to figure it out from scratch. It's slowing me down. But then again, rambling about the things I do to slow myself down is also slowing myself down. It's been a long day. Anyway, octahedral, typically 90 degrees. That lone pair is going to mess with it a little bit, so slightly less than 90 degrees. And final sheet, bond angles here. We've got... well, that's going to be square planar, so those are perfect 90-degree angles because the 2 lone pairs are going to cancel each other's repulsion effects out. And this one is a perfect 120. And there we go. So let me see what I have lined up next. Okay, let's take a look at big molecules. And then that'll be the last item I have for some of you. The rest of you will have to stick around for a while longer still. And I'll explain who has to stay and who has... well, you don't have to leave, but I'll explain who has to stay and who has the option of leaving after we cover this next problem. So, what happens when we're working with big molecules? Look at the molecule represented in problem 14 at the bottom of that clip. So, let's see. Methionine, which has that long formula, is an amino acid found in proteins. The Lewis structure is shown below. It's asking what's the hybridization type of each carbon, oxygen, and the nitrogen and the sulfur. So find the hybridizations of everything except for the hydrogens. Determine the hybridization of each of those atoms. And also what I would add to this is let's figure out the total number of sigma bonds and pi bonds in this molecule. And let's also determine all of the bond angles that we can figure out. So first I'm going to redraw the molecule. We have, let's see, hydrogen, carbon, hydrogen, hydrogen. Sulfur, and they've drawn 2 lone pairs on it. Carbon, hydrogen, hydrogen, another CH2, then a CHNH2, a CHNH2. Nitrogen has a lone pair. Then a C double O. And a C single O. And an H. All right, there's our big molecule. Let's figure out the hybridizations of each of the elements that are actually capable of hybridizing, so everything but the hydrogen. Carbon has 4 electron domains. That's sp3. Sulfur has 4 electron domains, 2 bonds and 2 lone pairs, so that's also sp3. Carbon, 4 bonds, sp3. Another sp3. Another sp3. Let's see, nitrogen has 3 bonds and 1 lone pair, so that's 4 electron domains total. That's sp3 again. This carbon has 3 electron domains. That's sp2. That's sp2. The oxygen has 3 electron domains, 2 lone pairs and 1 bonding domain. So 3 domains. This oxygen is also sp2 hybridized. And that makes sense because the oxygen has to have an unused p orbital to overlap with the unused p orbital of this carbon to make the double bond. So I guess what I'm trying to say is when you see double bonds or triple bonds, it's definitely not sp3. And it's definitely not anything past sp3. So if you see doubles or triples, sp3d is out of the picture, sp3d2 is out of the picture, and sp3 itself is out of the picture. So that's a little bit of a pro tip. This oxygen here, you've got 4 electron domains, 2 bonds and 2 lone pairs, so that's sp3. And the hydrogens can't hybridize, they just use their s orbitals to overlap with the, I guess all of these are sp3 orbitals that overlap with hydrogen. So yeah. Okay. Sigma and pi bonds. How many do we have? Well, I think for those who are paying attention, this is a pretty easy question when it comes to the number of pi bonds. It's just 1. We just have 1 pi bond, and we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. 19 sigma bonds and 1 pi bond. 19 sigma bonds and 1 pi bond. Okay. And what was the last thing? Bond angles. What are the bond angles? You can base it on the hybridization pretty much. All of the sp3s are around 109.5. For the sulfur, it's going to be a little less because of the lone pairs. And for this oxygen, it's going to be a little less because of the lone pairs. And for the nitrogen, it's going to be a little less because of the lone pair. But otherwise, your sp3s are going to have 109.5 degree bond angles for the most part. Your sp2s are going to have nearly 120 degrees for their bond angles. So these guys are going to have nearly 120. Well, I guess just the carbon actually would have nearly 120 degree bond angles. The oxygen isn't going to have any bond angles because there's only one bond. You can't find the angle between two bonds if you're not connected to two atoms via bonds. So yeah, the oxygen doesn't have bond angles. It's only connected to one other thing, which is carbon. So I guess you could argue that the oxygen has a 180 degree angle with just the carbon in that case. But yeah, ask your instructor what they want you to do in a situation like that, whether they want you to acknowledge that 2 points define a line and therefore make a 180 degree angle, or if they just don't care. Two different ways you could look at it. But yeah, this is the end for any high school students that are not taking IB chemistry and are fortunate enough to not have a chemistry teacher who is a sociopath. So if you're a high schooler not taking IB chemistry and you know your chemistry teacher is not a sociopath, you can stop watching at this point. You don't need to see what I'm going to cover in the rest of the video. If you are an IB chemistry student, you need to know some surface level details of what I'm about to discuss. I'm going to cover it in more detail than what you need to know. So don't be too intimidated, but I will give you more information than you need, way more. And if you are a high schooler with a sociopathic chemistry teacher, God help you, I'll try my best for you. And if you're a college student, you're sticking with me because they don't ignore this next topic in college. They usually insist on covering it. But yeah, if you aren't someone who needs to watch the rest of this video, you're free to leave or you're free to stay and just look at this. It wouldn't hurt to see what's coming up next, but be warned, it's complicated, it's messy, it's the stuff of nightmares. What's that one philosopher quote? What was it? Abandon all hope, ye who enter here, something like that. Was that from Dante's Inferno? I don't remember, but yeah, I know I'm making this out to be a really scary thing, and I guess if you overthink it, it can be quite intimidating, but it's really ugly and messy, and I don't see why they bother even trying to teach it when they know they're trying to teach it to students who don't have the mathematical know-how to fully appreciate and understand what's going on. I mean, they leave a lot out of it and really just cover the simplest cases for freshman college students, and I guess for IB chemistry students they make it even simpler. But even then, even when you simplify it in the case of the college students, it's still really hard to wrap your head around. Like, I wouldn't, if I was in charge of the curriculum, I wouldn't make students learn about this until they've had some linear algebra. And linear algebra is not the algebra of linear equations. It's an advanced course. You'd need to know lots of calculus before you get into the course. Not because you actually have to use calculus in linear algebra, but because the mathematical experience of a person who knows calculus is the kind of experience you need in order to study linear algebra. But now I'm rambling too much. For those of you who are forced to stay or haven't been intimidated, introducing molecular orbital theory. Molecular orbital theory. We're just going to scratch the surface of this. So, let me list what we are not going to cover, because even college professors know this is too much for you guys to handle. We are not going to cover no molecules with more than 2 atoms. We're not covering that. Too messy, too complicated. No molecules with more than 2 atoms. We're only going to focus on diatomic molecules. Also, no heteroatomic molecules, which is a fancy way of saying we're only going to look at molecules where the 2 atoms are the same kind of atom. So oxygen with oxygen, nitrogen with nitrogen, so on and so forth. So no heteroatomic molecules. Is heteroatomic the right word, or is it heteronuclear? Oh well, you know what I mean. So we're not going to mix and match atoms of different types, because that makes things messier. What else? What else? There was one more thing, if I recall correctly, and now it's escaped my mind. Think. So we're not going to do molecules with more than 2 atoms. We're not going to do heteroatomic molecules. And no atoms beyond second row of the periodic table. So we're not going to look past lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. We're not looking past those. Okay, so molecular orbital theory. First, let's start with the story of why we need it. So, the story of why we need molecular orbital theory. Let me switch these guys off first. Okay, and where's that? Turn that off. There we go. So, here's the story. Imagine, if you will, that you take some oxygen molecules, you cool them down, you pressurize them, you force them into the liquid state. So you've got liquid oxygen. You put it in a tube, you weigh it against a scale, you get its mass. Then you turn on a strong electromagnet. What happens if you expose the oxygen to that strong electromagnet? Remember how electrons have spin. Electrons have spin, which gives them a little bit of a magnetic field. Well, depending on whether or not you have paired or unpaired electrons in your molecule, that will determine how that molecule responds to a magnetic field. If all the electrons in your molecule are paired, then what we say about those molecules is that they are diamagnetic. They are diamagnetic, which means that they will create a weak magnetic field when they are subjected to a magnetic field, And the magnetic field that they create is opposite to the strong magnetic field that you expose them to in the first place. So if oxygen was diamagnetic, if the liquid oxygen in that tube was diamagnetic, you would expose it to that strong electromagnet. It would develop some magnetism that counters that electromagnet, and that liquid tube would be repelled away from the magnetic field. It would be repelled upward, and you would see the other side of the scale go down. It would seem as if the oxygen got lighter all of a sudden. On the other hand, if you have even one unpaired electron in your oxygen molecule, then your molecule is paramagnetic. Diamagnetism is really, really weak in comparison to paramagnetism. So the paramagnetism of even one unpaired electron will more than overshadow the diamagnetism of all the paired electrons that are in the molecule. So if you have even one unpaired electron, you have a molecule that's paramagnetic overall. Paramagnetism, while still weak, is way stronger than diamagnetism, and it does the opposite of diamagnetism. It responds to a magnetic field by being drawn closer to that magnetic field. So if oxygen is paramagnetic, it will actually kind of fall deeper into that magnetic field. It'll get closer to the bar magnet and tip the other side of the scale, I guess, higher, right? The oxygen in the tube would go down and the weights on the other side of the scale would go up, producing the illusion that the oxygen got heavier in the magnetic field. Well, oxygen turns out to be paramagnetic, and all the theories we've covered so far have no explanation as to why this happens. Oxygen happens to be paramagnetic, and we don't know why. Or at least we don't know why with the current theories that we have. So this is why we developed the need for molecular orbital theory. At least that's one of the things that molecular orbital theory accounts for. The other thing that molecular orbital theory accounts for is how you can have electrons that kind of aren't attached to any particular atom in a molecule, but kind of spread out over the whole molecule. In case you can't quite visualize what I'm trying to say here, remember from the previous video, I think we did the nitrate ion, and the nitrate ion had 3 resonance structures, or I guess 4 if you count the one that violates the octet rule. But the nitrate ion had 3 different resonance structures. I'm going to draw the other 2 without the lone pairs just to save time. So there's another one, and there's another one. There are 3 possible Lewis structures for the nitrate ion. So molecular orbital theory says it's none of these 3. It's actually a blend of all 3. And the 2 electrons in the pi bond that seems to be moving from one place to another across these different structures, those 2 electrons are basically shared across the whole entire molecule. There's like this orbital that covers the whole entire molecule, and the electrons kind of move in that space. The 2 electrons of the pi bond move around in that space. so that, you know, their what we call electron density is distributed about evenly across the whole molecule. So that's another thing that molecular orbital theory helps to address. Those are probably going to be the main highlights for the IB chemistry students. Let me see. There is this chart that lists some other comparisons. So let me see. Oh, before I pull up that chart, I should also mention these freely moving lone pairs, or not lone pairs, what am I saying? The freely moving electrons in the pi bonds, this pi bond that seems to jump around, the two electrons in there, the pi electrons, are said to be delocalized. Delocalized pi electrons are what you have in that pi bond. That pi bond is not fixed to a specific place because there are 3 potential places it could be, so the electrons of that pi bond are not localized, not fixed to a specific location. We call those delocalized electrons. And all the other electrons don't have freedom of movement across the molecule. The lone pairs around this oxygen, for example, those are localized electrons. They don't get to, you know, move around the molecule. They're stuck with the oxygen that they're stuck to. The electrons in the sigma bonds are going to be localized. They don't get to move around. It's just those 2 electrons. They can sometimes be here, they can sometimes be here, they can sometimes be here. So those are delocalized versus localized electrons. Anyway, let's pull up this comparison chart. So this chart compares valence bond theory with molecular orbital theory, and valence bond theory, in this chart at least, it also includes hybridization theory. So yeah, basic comparison chart. Valence bond theory considers bonds to be localized between one pair of atoms, which is not always going to be the case. Molecular orbital theory considers electrons to be delocalized throughout the entire molecule if need be. Valence bond theory, of course, is all about overlap. We've talked about that. Molecular orbital theory is also about overlap. Well, actually, let me think here. How do I want to say this? We're going to see the role of overlap in molecular orbital theory pretty soon, but the difference is that for molecular orbital theory, overlap determines how you make your molecular orbitals, whereas for valence bond theory, overlap determines how you make your bonds. So that's the key difference between how the 2 theories treat overlap. With valence bond theory, you've got sigma and pi bonds. With molecular orbital theories, you've got bonding and anti-bonding interactions. Basically, we'll see once we look at a molecular orbital diagram what all this is about. I probably should have saved this table for after introducing some more of the basics of MO theory. Let's see, what else? Valence bond theory predicts shape based on the number of regions. And molecular orbital theory, well, molecular orbital theory just kind of gives you the shape of the molecular orbital, which essentially is the shape of the molecule. Because molecular orbitals are these orbitals that span the whole entire molecule, so their shape kind of determines the distribution of electrons throughout the molecule. And yeah, the main weakness of valence bond theory, that's the one I highlighted. In valence bond theory, you need multiple structures to describe resonance. We draw multiple resonance structures because we just don't have the ability to illustrate the idea that you might have some delocalized electrons that can be in more than one location at different times and kind of are randomly moving about all of the different locations where they potentially could be. So for that, we have to draw a bunch of different resonance structures and say that the actual molecule is some blend of the 2, 3, 4, 5, however many resonance structures you have. I'm probably not wording all that very well. But let's dig deeper into molecular orbital theory and figure out the basics of it. Do I want to... Well, yeah, let's start with this. So, in the figure you see in front of you, this is an idea that you might be familiar with if you've already done physics. If you haven't done physics, basically, this illustrates what's known as wave interference. This is what happens when two waves come into contact with each other. Sometimes two waves can come into contact with each other in such a way that their peaks and valleys match up, in which case the two waves just add up. That's what's called constructive interference, and you just get a bigger wave as a result. Other times, like in the right-hand side of the figure, you might have waves that line up in such a way that the peaks of one wave line up exactly with the valleys of another wave, and vice versa, and when both of those waves are in the same place at the same time, they cancel each other out. And that's how you get that flat line on the far right side of the figure. So you might remember that orbitals basically describe the shape of space in which the probability of finding an electron is most likely, and you might remember those radial probability functions that we drew, which kind of looked like waves themselves. If you remember the one for the s orbital, for the 1s orbital, it looked like this. For the 2s orbital, it looked like this, and so on and so forth. Basically, the height is the probability of finding an electron, and the x-axis or horizontal axis represented the distance from the nucleus. So in the 1s orbital, represented by that black peak, you were most likely to find an electron around this distance from the nucleus, whatever that number is, however many angstroms that is. And with the 2s orbital, represented by this set of waves, your most likely place to find an electron was somewhere between this far away and that far away from the nucleus. And then your next best shot at finding an electron was around here. Basically, what I'm trying to say is, without going into too much detail, orbitals have some wave-like properties to them. The behavior of orbitals can sometimes be similar to the behavior of waves. So orbitals can interfere with each other kind of the same way that waves do. And so orbitals can interfere with each other constructively or destructively. Orbitals can overlap in such a way that they add, and they can overlap in such a way that they subtract. So if I take an s orbital, if I take an s orbital, let's say it's a hydrogen, for example, and another s orbital from another hydrogen, and I let them overlap like that, they could add, they could subtract in the place where they overlap. Where they add, you would get essentially this sort of mixed potato-shaped region of space holding electrons. And where they subtract, you would basically just create a gap here where everything canceled out, and you're left with, I guess, the parts that didn't get canceled out. So this is the result of constructive interference, where they add. Constructive interference. And this over here is the result of destructive interference when the orbitals overlap. Destructive interference. And I see this lime green marker is just about dead. It probably still looks fine to you guys because I look at the videos afterwards and I guess maybe the camera angle makes it more readable, but from what I'm seeing, it's definitely starting to fade. Anyway, where was I? So, yeah, you can get constructive interference, or you can get destructive interference, or you can get both. So, remember when we mixed s and p orbitals to make hybrid orbitals, we said that the rule was you can blend together orbitals, as many orbitals as you want, as long as you give back the same number of orbitals, and the total energy of the orbitals is the same. So with sp3 hybridization, we showed that you can take an s orbital and 3 p orbitals and blend them together and replace them with a set of sp3 orbitals that have the same total energy. I think the made-up numbers that I used to help illustrate this point were 9 energy units for s and 15 for each of the p's. And if you mix them and blend them together, that's a total of 45 plus 9 is 56, over 4 is 14, right? So each of these was 14 energy units. What if I did the opposite? What if I go in the other direction? What if I take a bunch of orbitals that are equal in energy and I put them together, and then I make some orbitals that are higher in energy and some orbitals that are lower? What if I could take my sp3 orbitals and make completely new orbitals, not even s or p orbitals, just something completely new? Let's say each of these, of course, have 14 energy units based on the made-up numbers that I have. What if I say blend all 4 of these, so I've got a total of 56, and I split it into, let's say, 2 orbitals here and 2 orbitals here. like so. And let's say that, for example, I distribute them by having these two new orbitals being 7 more than the originals and these two being 7 less. Let's say I go with 7 and 7. Let's say that 2 of the orbitals gain 7 energy units, so they become orbitals with an energy of 21, and 2 of the orbitals lose 7 energy units to compensate, leaving you with a pair of orbitals with energies of 7 and 7. The total is still 56. The total is still 56. 7 plus 21 is 28, and then times 2, yeah, that's 56. So yeah, I can go both ways. I can take orbitals that have different energies, put them together and make orbitals that have the same energy, but I can also do the reverse. I can take orbitals with the same or similar energies and blend them together to make orbitals that are higher or lower in energy. I can go in both directions. And no matter which direction you're going, this is what's called a linear combination. Linear combination of orbitals. Linear combination of orbitals. Or, I guess, linear combination of atomic orbitals. And the term linear combination is something you're going to hear a lot if you ever take a linear algebra class in college, or maybe in a sort of advanced high school class. If you actually are fortunate enough to go to a high school that offers linear algebra, then yeah, you'll encounter the term linear combination, and you'll get a better sense of what it means when you take the corresponding math classes, but hopefully this gives you a general idea of it. The math basically says that any linear combination of the orbitals should work. At least that's my understanding of it. So you can go in both directions. You can do pretty much whatever as long as you end up with the same total number of orbitals and the same total energy for those orbitals. As long as you do that, everything goes. So I have here the first type of molecular orbital that we can make. It's basically what I just drew, but fancier. Yeah, that diagram shows you a pair of s orbitals. They combine together, and depending on the amount of overlap, you can figure out what that amount is, subtract it in one case, and add it in the other case, and you get 2 new molecular orbitals. The one with lower energy, the result of adding the overlap region, is called the bonding orbital, while the subtraction product is called the antibonding orbital. And note that add and subtract in that figure, they refer to adding and subtracting the overlap region, not the energy. Notice that the subtraction product is the one that's higher in energy, while the addition product is the one that's lower in energy. So let's try, I guess, putting numbers to it to kind of drive the point home. Let's say I already declared that s orbitals have an energy of 9, but I guess in my example this would be a 2s orbital. Let's say, and I'll do this on a new sheet, let's say that for my hydrogens, let's say I have the s orbital of one hydrogen and the s orbital of another hydrogen, and let's say they're at an energy of 5. And let's say they overlap with each other, and the extent of the overlap, the size of the overlap, is equivalent to 3 units of energy. In that case, when I blend these s orbitals together, I can make an orbital that's 3 units more in energy and an orbital that's 3 units less in energy. So let me mark a 2 here and an 8 here. I think that's symmetrical. And yeah, so over here I would get this new orbital, this bonding molecular orbital as it's called. We call it a bonding MO for short. And over here we would get the higher energy anti-bonding MO. Anti-bonding MO. I don't think you need the dash, but yeah, so 5 plus 5 is the same as 8 plus 2. So total energy is the same. We haven't broken that rule. And 2 orbitals in, 2 orbitals out. What's the difference between this and the hybrid orbitals we were talking about in the earlier parts of the video? Well, hybrid orbitals are a result of mixing orbitals that are from the same atom. Here we're mixing orbitals from 2 different atoms. So that's one key difference between molecular orbitals and hybrid orbitals. Hybrid orbitals are atomic orbitals. They belong to the same atom that contributed all of the orbitals that went into hybridization in the first place. Whereas here, the contributions are coming from different atoms. And no, I'll leave that comment out for now. We'll talk about that later. So, yeah, you end up with, I guess you can match this diagram to what we've got over here. So you've got the bonding molecular orbital. When the overlap region is included, that results in a decrease in energy. When the overlap region is subtracted, that results in an increase in energy. And so you end up with 2 orbitals, one that's a little higher in energy and one that's a little lower in energy than the original orbitals. This can be very beneficial, especially in the case of hydrogen, our first example. I'm talking about specifically hydrogen gas, diatomic hydrogen, H2. Why would hydrogen benefit here? Because if you simply did valence bond theory, if you simply overlapped 2 s orbitals directly and formed a sigma bond, then those 2 electrons would still be at an energy of 5. But if instead you allow the 2 hydrogens to mix their orbitals together to make this higher energy anti-bonding orbital and this lower energy bonding orbital, then the 2 electrons that the hydrogens have can go down to this lower energy, leading to a more stable molecule. And then the anti-bonding molecular orbital, sure, it's higher in energy, but if there are no electrons in it, then no problem. So that's one of the added benefits of making molecular orbitals. You get to make more stable molecules because you get to put the electrons in lower energy orbitals. Potentially. It depends on how many electrons you have. If I had more than 2 electrons here, then I'd be forced to start putting electrons into this costly anti-bonding orbital. Let's say I had the H2 plus ion, in which case I guess one hydrogen brings in a single electron. Wait, H2 plus? No, H2 minus. That's one extra electron. If I had the H2 minus ion, then I would have one hydrogen bringing in 2 electrons, so let's say it's this one, and the other one bringing in just 1 electron, so I'd have 3 electrons total. So I guess 2 electrons go there and 1 goes up here. Is that still better off than what we started with? Let's see. So 2 electrons at an energy of 5 and a third electron at an energy of 5. That's a total energy of 15. Versus 2 electrons at 2 and 1 electron at 8. So 4 plus 8, that's 12. Oh, that's less. So we still benefit from doing this. We still have a lower total energy. And if you're wondering about the extra energy from having electrons paired up, well, that hasn't changed because originally these 2 electrons were paired up. They're still paired up here. So even if you took the extra energy for pairing into account, if, say, I add, I don't know, 1 unit of energy due to pairing up electrons here, then the total before making molecular orbitals would be 15 plus 1 is 16, and after it would be 12 plus 1 is 13. So it doesn't matter if it's plus 1 to both situations. I probably didn't word that very clearly, but you can rewind that part of the video and play me on repeat until it starts to make sense. This stuff doesn't really make all that much sense. It's a really messy topic, and I understand it on such an abstract level that I have a hard time explaining it, especially to a microphone that can't ask me questions and help me figure out what I need to clarify. So I hope you'll forgive me if this isn't exactly my peak performance. Okay, so it seems like we benefit from doing this energy-wise, but only up to a certain point. What if I had helium? What if I was working with helium instead of hydrogen? What if I was working with helium instead of hydrogen? Let's say there's a hypothetical helium molecule, a helium bonded to another helium. So each helium comes in with 2 electrons in its 1s orbital. So here's helium number 1. It brings in 2 electrons. Here's helium number 2. It brings in 2 electrons. Okay, and suppose I make these molecular orbitals. Suppose I make these molecular orbitals, so subtract some to make this one and add an equivalent amount to make this one. Let's just go with the same numbers we had before, 5, 8, and 2. Don't take these numbers too literally. Again, these are just numbers I'm making up to kind of help the idea become more concrete. Okay, well, I can send 2 electrons down to here, and I can send 2 electrons down to here. I have 4 electrons to distribute, so 2 of them are going to go here, and then the other 2 have to go here. We lost any benefit we could have had from making molecular orbitals, because now the total energy of the electrons is the same as it was before, right? Originally, you had 2 separate helium atoms with 5 and 5 plus pairing energy, if you want to take that into account, and 5 and 5 plus pairing. And, well, what do we have now? 2 and 2 plus pairing and 8 and 8 plus pairing. That's the same sum. 5 and 5 and 5 and 5 plus the pairing energies would be 10 here and 10 here, so 20 plus extra for pairing. And over here, 2 and 2 with 8 and 8, that's also 20. 2 plus 2 is 4, 8 plus 8 is 16. That's also 20 plus, of course, 2 pairing energies. So you lost any benefit that you got from creating this lower energy bonding molecular orbital if you have to put a bunch of electrons in the anti-bonding molecular orbital anyway. So this only leads to more stable molecules in the event where the number of electrons that you can put into bonding molecular orbitals is greater than the number of electrons that you have to put in anti-bonding molecular orbitals. The less electrons you have to put in here, and the more you get to put in here, the greater the added stability from making this low energy orbital. So there's something you can calculate called bond order. And you've heard me use this word before. I think I said it a number of times in the previous video. So bond order can mean different things in different contexts. Bond order, in my use of it for the previous video, the way I was using it, referred to just the number of bonds. A bond order of 1 is a single bond, a bond order of 2 is a double bond, a bond order of 3 is a triple bond. But in molecular orbital theory, bond order can sometimes be a fraction. It can be 0, it can be 1/2, it can be 1, it can be 1.5, it can be anything up to 3. So it's kind of related, except that unlike my previous usage of this term, in molecular orbital theory, bond order can be fractional. So how do we determine bond order? Really, really simple. You take the total number of bonding electrons. You take the total number of bonding electrons minus the total number of anti-bonding electrons. Anti-bonding electrons. And then divide all that by 2. You take the total number of bonding electrons minus the total number of anti-bonding electrons and divide that by 2. The bonding electrons are your cheap electrons in terms of energy. They're the ones that you get to put in the bonding molecular orbital. They're the ones that have a low energy. The more of those, the better. The more bonding electrons, the more your bonding order. The anti-bonding electrons are the costly ones. They're the ones that you have to put in that really high energy orbital. Those are the ones that you want to not have so many of. So the more bonding electrons and the less anti-bonding, the greater the number you get from subtracting bonding minus anti-bonding. The larger that number is, the greater the bond order, and also the greater the stability of the bond, the greater the stability of the molecule as a whole. So helium-2, diatomic helium, is not stable because it has a bond order of 0. You've got 2 electrons in the bonding MO, and you've got 2 in the anti-bonding. So that's 2 minus 2 is 0 over 2, which is 0. So helium has a bond order of 0. Bond order of 0. And a bond order of 0 is essentially not having a bond at all. The diatomic helium molecule is not a stable molecule. It's not likely to exist in nature. You would need to supply energy to force it to come into existence in the lab, if you ever had a reason to forcibly make diatomic helium. On the other hand, this ion over here, H2-, this is somewhat stable. This is somewhat stable because what's its bond order? You've got 2 bonding electrons minus 1 anti-bonding electron. So that's 2 minus 1 is 1, divided by 2 is 1/2. So it's about as stable as something with a 50% covalent bond, if that makes any sense. So it's definitely less stable than a single bond with a bond order of 1, but it's still better than 0. So this ion, this diatomic hydride ion, I guess is what I'll call it, can be made. It does have some semblance of stability to it. It would be more stable if I just did plain old hydrogen gas. Regular hydrogen gas would be basically remove this electron, and then you'd have 2 bonding minus 0 antibonding over 2 is equal to 1. So yeah, regular H2 would have a bond order of 1. Would have a bond order... I did not spell that right. Would have a bond order of 1. So that's regular H2. And you will find when calculating bond order that it's going to be consistent with some molecules you're already familiar with. The bond order of diatomic oxygen gas, for example, is going to be 2. And if you know your diatomic oxygen gas, its Lewis structure does suggest that it's got a double bond. So yeah, molecular orbital theory does indeed give us a bond order of 2 for oxygen gas. It gives us a bond order of 3 for nitrogen gas. So it is still consistent with our previous definition of bond order. It just includes more stuff that our previous definition didn't cover. Anyway, so far I've been talking about the molecular orbitals formed by the combination of s orbitals from 2 different atoms. What about the combination of p orbitals? Oh, and before that, let me talk about the names of these orbitals. So s orbitals will overlap directly, so they form a sigma bond. So molecular orbitals that are formed from direct overlap are sigma bonding molecular orbitals and sigma antibonding molecular orbitals. So the name of this molecular orbital is called the sigma s orbital. And this orbital over here, this molecular orbital, is called the sigma s star, and the star indicates that it's the antibonding molecular orbital due to the result of direct overlap, sigma overlap, of s orbitals. And if you want to be more specific, I guess you could call this sigma 1s and sigma 1s star, because the orbitals that we mixed in this case were 1s orbitals. They came from the first shell. But maybe that's getting too detailed. Okay, so let's take a look at p orbital overlap and the molecular orbitals you can make out of those. So p orbitals can overlap directly. They can also overlap indirectly. For direct overlap, there you go in that figure. Those are the 2 different shapes that you can get. The bonding molecular orbital for the overlap of 2 p orbitals is the one you see in the top, and the one that you see in the bottom is the antibonding version. It does also have that star, as I showed a few minutes ago. So that's what tells you, in case you couldn't tell which one was which, the star tells you that's the anti-bonding version. So that's the one that's higher in energy. But yeah, so that's the direct overlap of p orbitals. Those are the sigma molecular orbitals that you can make out of them. But two of your p orbitals have the ability to overlap indirectly. They can make pi molecular orbitals. And here's what those would look like. So for indirect overlap, they can overlap out of phase, which is what they show you at the top. So they've got the red overlapping with the blue lobes. The red lobe of one p orbital is overlapping with the blue lobe of another p orbital. That's them basically saying that the peaks are lining up with valleys, if you think of it in terms of waves, resulting in destructive interference, creating subtraction, which leads to an emptied out space in between them, which is what you see, to the right in the top right corner there. And of course, if they just directly overlap, if they overlap, or not directly, if they indirectly overlap in phase, so they have constructive interference, they add to each other, and the region of overlap kind of becomes part of the new molecular orbital. That's the bonding version that you have in the bottom right. You're not expected to be able to figure out these shapes on your own. If you have to know the shapes, just memorize them from these figures if you have an instructor that insists on that, but you're not expected to be able to look at these and predict exactly what the molecular orbitals are going to look like. That's too messy. So don't freak out too much about that. But yeah, there you go. So those are pi p molecular orbitals and pi p star molecular orbitals. And you can get two sets of those. You can get two sets of those because you have two p orbitals that can create pi bonds. If you have one p orbital creating a sigma bond, the other two have to make pi bonds, so you actually have two sets of these. Okay, now that we have added p orbitals to the mix, let's take a look at what our molecular orbital energy diagram looks like. So what you have in front of you is the standard energy diagram for molecular orbitals that result from the bonding of two atoms from the second row of the periodic table. So the bottom part of this diagram is stuff we've already seen. We've already seen what happens with the s orbitals. You put them together, you create two new molecular orbitals, one that's lower, one that's higher in energy than the originals. That's stuff that we've already seen. And then for the top half of that diagram, this is where we see some new stuff. Let's take a look at this a little more closely and explain what's going on in case it's not readily apparent. So if I'm going to leave the s orbitals out of it because we've already covered those. If I have a set of p orbitals, so here's one set of p orbitals from one atom, here's a set of p orbitals from another atom. P orbitals from atom 1, p orbitals from atom 2. And then here's where I'm going to draw the new molecular orbitals that are made out of them. Okay, so one of these p orbitals overlaps directly with one of these p orbitals. Direct overlap achieves maximum overlap. The greater the amount of overlap, the farther in energy the two molecular orbitals are going to be. The more overlap, the more energy subtracted, and also the more energy added when you make the bonding and anti-bonding molecular orbital. So for the ones that overlap directly, the bonding molecular orbital is going to be way, way lower in energy, like say around here. So that's from the direct overlap. And the anti-bonding molecular orbital that they make is going to be way, way higher in energy, because there's lots of overlap going on here. It's direct overlap, which leads to a lot of overlap. Basically, the greater the amount of overlap, the larger this gap right here, the greater the size of this gap. I don't want to draw on top of it because I'm going to put more things in there. And let me actually change these colors to improve the visibility. Yeah, I'll just do that. Okay, so that's two of the p orbitals overlapping directly. The bonding molecular orbital that they make is the sigma p, specifically the sigma 2p molecular orbital, and the anti-bonding one is the sigma 2p star. What about the other two p orbitals? So I guess I'll check these two off to say that I've already used them. The remaining p orbitals need to overlap indirectly. They have no choice. We discussed this. If two of your p orbitals overlap directly, then the other p orbitals are perpendicular to them and they can't overlap directly. They have no choice but to overlap side to side. So this p orbital over here goes with this p orbital. They overlap indirectly. And because they overlap indirectly, the size of the overlap is smaller than it was for the first two p orbitals. There's less overlap, so these two don't go as far. They don't split up as much as the first pair of p orbitals that I did. So that goes to there, and let's see. Gotta try and keep it symmetric here. Those go to there. So that takes care of those two p orbitals, but it also accounts for those two p orbitals because they also overlap side to side, and they'd have the same size of overlap. So in fact, all four of the remaining p orbitals, in two separate pairs, of course, will create two bonding orbitals here and two anti-bonding orbitals here. So here you've got a pair of pi 2p bonding molecular orbitals. Here you've got a pair of pi 2p star anti-bonding molecular orbitals. And there you have it. So the the molecular orbitals that result from the indirectly overlapping p orbitals have a smaller gap size. They don't drift as far away from the original energy of the p orbitals due to having less overlap. At least That's what's normally supposed to happen. Oh, just you wait. We're going to abandon this, or, well, modify it significantly later on. But let's take a look at some second row elements. And actually, let's look at oxygen. Let's look at the oxygen molecule specifically and find our explanation as to why oxygen is paramagnetic, not diamagnetic. Let's take a look at that. So I'm going to, should I do it on this diagram? No, I'll do it on a separate one. I'll do it on a whole new diagram. So let's see. I'll have there's energy there. So oxygen has, I'm going to ignore the 1s orbital and just focus on the 2s. So there's one oxygen, there's another oxygen, there's the 2s and 2s, and there's the 2p and 2p for the other oxygen. And I guess you could draw the electron diagram for oxygen if you really wanted to. But it's not entirely necessary because we're tallying up the valence electrons and putting them into the molecular orbitals according to the Aufbau principle and Hund's rule, and it doesn't matter where they were originally in the oxygen atoms before bonding, so it's not worth our time. But you could definitely, fill in oxygen as 2s2, 2p4. You could do this if you wanted to, but again, it's not worth your time because you're grabbing all these and putting them into the new orbitals anyway. But yeah, so our 2s orbitals, they overlap directly. That's the only way they can overlap. So they form the sigma 2s bonding molecular orbital, and the, let me draw a dotted line there to help me try and draw it to scale, the sigma 2s star anti-bonding orbital. Then for the p's, first you've got the direct overlap, which will, let's say the sigma 2p is over here. Oh, I'm not going to have space to draw my electrons, am I? I'll just use different colors. So I'm going to have the sigma 2p down here, and then I guess my sigma 2p star will be up here. So those are bonding and anti-bonding orbitals resulting from direct overlap, and then from the indirect overlap we're going to get pairs of bonding molecular orbitals, so one pair of pi 2p molecular orbitals and one pair of pi 2p star molecular orbitals. Okay, and we have how many electrons that we need to distribute into these orbitals. We've got 2, 4, 6 electrons here and 6 electrons there. We've got 12 electrons to work with. So Aufbau principle, fill from lowest energy to highest energy. Hund's rule, first fill them out in parallel and then pair them up only when necessary. And I guess Pauli exclusion principle, if you pair up electrons, make sure they have opposite spins. So 12 electrons. Here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Ah, we have some unpaired electrons in the O2 molecule. This was oxygen, this was oxygen, this is the O2 molecule. We have some unpaired electrons in our O2 molecule. This explains why oxygen is paramagnetic. This explains the paramagnetism of oxygen. This is something valence bond theory did not have an answer to. Molecular orbital theory seems to have an explanation. This is why we have some faith in it. It's still messy and complicated, and it's the stuff of nightmares, but it helps explain stuff. So there you go. What was I going to say next? Bond order. Let's figure out the bond order. So number of electrons in bonding orbitals minus number of electrons in anti-bonding orbitals. So non-star electrons minus star electrons, if you want to look at it that way instead. So I've got, and ignore these. These were the electrons of the original atoms. We're talking about the electrons of the molecule now that the atoms have been combined. So just looking at these, we've got, let's see, where are my starred ones? So that is a starred orbital, that is a starred orbital, and that is a starred orbital. Let's see, so my non-stars, I've got 1, 2, 3, 4, 5, 6, 7, 8, and that's it. So I've got 8 bonding electrons minus 1, 2, and 3 and 4. 8 minus 4. So 8 bonding electrons minus 4 anti-bonding electrons. Divide all that by 2. 8 minus 4 is 4. 4 over 2 is 2. The bond order is 2. This would suggest that the oxygen molecule probably has a double bond, which it does. So there you go. There's the example of oxygen. Now, this also works for fluorine and neon as well. It works just fine for fluorine and neon. The diagram, as we've currently structured it, is perfectly fine. It's not so fine for boron, carbon, nitrogen. In fact, any of the second row elements before oxygen, the diagram as we have it set up right now is not in the correct order. Oh yeah, more layers of complexity are coming. You thought this was over. We haven't even started yet. I mean, I feel like I've covered most of what I want to show, but yeah, let me pull up this image for you to show you what all the second row elements do. So, with oxygen, fluorine, and neon, you have the pattern going from bottom to top of 1 bar, 1 bar, 1 bar, double bar, single bar. If you read it from top to bottom, that's how it goes for oxygen, fluorine, and neon. However, for nitrogen and everything before nitrogen, there seems to be a bit of a switch. It starts looking more like a, what do you call that game? Hopscotch pattern, right? That looks like hopscotch. Am I the only one who's reminded of hopscotch when looking at that? Please tell me I'm not the only one. Anyway, there's this weird switch that happens. And why on earth is this switch happening? What's going on? What's shifting the energies of these molecular orbitals out of the place where we would expect them to be? Well, there's some interference that we haven't taken into account. Remember the rule that said the more the orbitals overlap, the farther apart they are on the energy diagram? We just used that rule a couple times. It should be in recent memory. The more two orbitals overlap, the farther apart they will be in energy when you blend them into molecular orbitals. So what happens then when you've got a significant amount of overlap between an s orbital and a p orbital? Of course, they're not going to blend together to make a molecular orbital because they're not of the same type. I don't know if orbitals of different types can mix to make molecular orbitals. I never really dug that deep into molecular orbital theory, but if I don't know it, then you definitely don't need to know it. If I completed a minor in chemistry without ever needing to know that, you certainly don't need to know that for general chemistry. Went off on a tangent and lost my train of thought. Where was I going? Oh, right. So there is some interference between the s orbitals and p orbitals in some of those molecules. Specifically, what you notice about the ones that seem to have a problem, lithium, beryllium, boron, carbon, nitrogen, those are all further to the left. What do we know about atoms that are further to the left in a row on the periodic table? If elements are in the same row, the ones that are further to the left are larger in size. Yeah, lithium is bigger than beryllium, which is bigger than boron, which is bigger than carbon, bigger than nitrogen, bigger than oxygen, fluorine, neon. So that's the size ordering. And of course, the bigger atoms also have bigger orbitals. Bigger orbitals overlap more. So what's happening is, picture this. Picture this. You've got two atoms that are trying to overlap. They overlap their s orbitals, but they also overlap their p orbitals. Two of their p orbitals overlap directly, so there's one p orbital for one of the atoms, and I guess I'll use a different color to draw the other p orbital. And then there's another p orbital for one of the other atoms. Okay, so yeah, the p orbitals here are not just overlapping each other, they're also overlapping the s orbitals of the other atom. Ooh, so then, and this is specifically for the sigma bonding ones, the pi bonding p orbitals aren't affected by this, or at least they're not as significantly affected. Let me do it in orange. Let's say, for example, I draw the y-axis p orbital of this atom and the y-axis p orbital of that atom. So when they overlap with each other over here, there isn't much interference from these s orbitals. I mean, there might be some, but it's going to be a very tiny amount. So these perpendicular p orbitals, the one on the y-axis and the one on the z-axis, they're not going to be very affected by this. But the sigma bonding p orbitals, oh, those are going to be significantly affected. And the bigger the atom is, the more significant the effect is. So, here's what happens. Take our molecular orbital energy diagram the way that it should be, quote unquote should be. So take the energy diagram that we had before, basically just copy what we had back here, the somewhat symmetric pattern. So I guess I'll draw, okay, an S and 3 P's and 3 P's there and an S there. Okay, good. So take what we expect to see normally. So we've got that, and then in the other direction we've got this. I feel like I've already spaced these out too far. Yeah, I think I might have, but I'll keep going. And then here I'd expect the sigma bonding p orbitals to go down to there. And I guess that would take them up to here. Yeah, I definitely didn't make good use of my space. I could have drawn these p orbitals a little higher, and that would have looked nicer. But oh well, missed opportunities. Okay, so those are the sigma 2p's, and I should probably label them as a... No, I'll label them after. And then the pi 2p's, this is where we expect to see them. Oh, I did not draw that well, did I? Yeah, that's supposed to go down to... You know what? I'll start over. Probably should have done that as soon as I realized my p orbitals were drawn too low. Okay. There's your energy axis. So I'll put my s orbitals there. And then my p orbitals, I'll put them way up here. Yeah, I think that'll be good. And then there we go. That takes care of that. All right. Now then, drawing my diagrams. So I'll have... I guess I'll draw one here, and then, yeah, I'll just use the midline technique. I think it's faster. So roughly there. Okay, that's the sigma 2s and the sigma 2s star. And then for my p's, let's see, sigma 2p, I would expect it to be around here. And then I guess sigma 2p star would be up there. So sigma 2p, sigma 2p star up there. And then my pi 2p's, I would expect them to be here and here. I would expect them to be there. So let's see, that's pi 2p bonding, and then pi 2p anti-bonding. Okay, so that's the normal state of affairs. But what happens when there's a lot of overlap between the s and p orbitals that are trying to sigma bond? Well, they're going to try and get farther apart from each other. So what's going to happen is that the sigma 2p and also the sigma 2p star, both of the sigma molecular orbitals for 2p, are going to try and get farther away in energy from the sigma 2s and the sigma 2s star. So I guess let me mark them in navy blue. So these guys are going to try to get further away in terms of energy from these guys. How do they get further away from each other? Well, for these guys to get further away, they can just go up. If they go down, they'll get closer. We don't want that, so they'll have to go up. For these guys to get away from these guys, they'll have to go down. So these guys go down a bit, and the new locations of the sigma 2s and the sigma 2s star are just a little bit lower. So sigma 2s star will end up here, and sigma 2s will end up, I don't know, here, for example. Meanwhile, the sigma 2p and the sigma 2p star, they're going to go up. Sigma 2p star is going to go so high up it goes off the page. Let me actually make use of this page that otherwise would have gone to waste. So sigma 2p star is going to go up to like here. And sigma 2p, it's going to go up past the pi 2p. And that's what's going on. That's what's going on. So the end result is you have a diagram that has the sigma 2p at a higher energy than the pi 2p. So the pi 2p ends up getting filled first for lithium through nitrogen. For lithium through nitrogen, the pi 2p gets filled before the sigma 2p because the sigma 2p goes up in energy to get away from the sigma 2s orbitals so high up that it surpasses the pi 2p. So that's what's going on there. And oh boy, is this hard to remember. Like this explanation, you might be nodding right now and saying this makes perfect sense, but good luck remembering this and trying to put those words together on an exam that asks you to explain why lithium through nitrogen don't have their orbital diagram follow the same pattern as oxygen through neon. Good luck remembering those words. Anyway, now that we know this about lithium through nitrogen, let's try drawing the orbital diagram, the molecular orbital diagram rather, for nitrogen. Let's do it for nitrogen, just so that we can see how this changes things, if it changes anything at all. Let's compare it with what we would normally expect. So I'm going to skip on, drawing the original orbitals on the side. I think I've done that enough times at this point, and I'm just going to skip ahead to drawing the molecular orbitals. So I'm going to draw two separate energy diagrams, one that's, the traditional, or should I call it traditional? Yeah, let's call it the traditional, unofficial term here, but let's say this is the traditional case. This is expectations. Yeah, that's a better word. Expectations versus reality. Expected versus reality. Okay. let me see. So the expected pattern is, it kind of looks like a tree, I guess, or a club. So you've got the sigma 2s and the sigma 2s star and the sigma 2p and then the pi 2p, two of them, and then the pi 2p star, pi 2p star, and then the sigma 2p star. Okay, so that's expectations versus reality is more like this. These two are a bit lower, so sigma 2s star, I'll put it there, and sigma 2s, I'll put it like down here. And then sigma 2p shifts up so that pi 2p actually ends up lower than it, so pi 2p is still here, but sigma 2p is around here, and then pi 2p star is still where it always was, so that's pi 2p star. I really messed that one up, and I probably drew them too close to each other, and then sigma 2p star gets pushed further up, so it's like there. Okay, and I said I was looking at nitrogen specifically. I was looking at N2, so I'm looking at the nitrogen molecule. How many electrons in the 2s and 2p orbitals of a nitrogen atom? That's the valence electrons of nitrogen. There's 5. So 2 nitrogen atoms would have 10 electrons for us to work with. Okay? So expectation, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Reality, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, not very consequential. In the end, nitrogen is diamagnetic. Bond order is still going to be the same, it looks like, because yeah, even if I filled them in a different order, they're still bonding orbitals, so it's not going to affect bond order. Okay, let me see if I can dig up another example where this would make a difference. Let's take a look at carbon. Let's take a look at the case of C2. Let's take a look at the case of the C2 molecule. I probably should have went with that in the first place. But let's calculate bond order of nitrogen real quick. So we've got how many bonding electrons? We've got 2 here, plus 2 here, plus 4 here, so that's 8. And we have 2 anti-bonding electrons, so 8 minus 2 is 6. Divided by 2 is 3. A bond order of 3, which is exactly what we expect for the nitrogen gas molecule. After all, this is its Lewis structure. We expect a triple bond. And that's going to be the same regardless of which diagram you use, because it's still 8 minus 2 either way. Let's take a look at expectations versus reality for C2. Let's take a look at expectations versus reality for C2. Okay, so we've got sigma 2s, sigma 2s star, sigma 2p, I guess I'll draw it lower this time, sigma 2p, pi 2p, yeah, I'll just draw it right here. Actually, fine. I'll draw pi 2p over here, and then pi 2p star over here. And sigma 2p star up there. Okay, so that's expectations versus reality. Sigma 2s is down there. Sigma 2s star is like here. Sigma 2p is further up, so I guess pi 2p comes first. So there's pi 2p, and then sigma 2p is somewhere in here, and then pi 2p star is right after it. Pi 2p star. Maybe I should, yeah, let's make them longer so that they look closer. And then sigma 2p star is all the way up there. Okay. So if we look at the C2 hypothetical molecule, let's see what difference this makes. I expect this will make a difference in terms of the magnetism that we observe. So expectation says, let's see, carbon has 4 valence electrons, so 2 of them would have a total of 8. So that's 1, 2, 3, 4, 5, 6, 7, 8. That's expectations. Versus reality, 1, 2, 3, 4, 5, 6, 7, 8. Ah, for the C2 molecule, this makes all the difference. Paramagnetic versus diamagnetic. So we know that this sp mixing thing that pushes the sigma 2p up past the pi 2p, we know this is a real thing because we can look at the C2 molecule and observe that it behaves like a diamagnetic material, not a paramagnetic material. So that just further reinforces the idea that molecular orbital theory seems to make sense. Okay, I think that's pretty much it for molecular orbital theory. The only thing I have left to show you is that you can write electron configurations in terms of molecular orbitals. The same way that we can write molecular, or did I say molecular? Electron. The same way that we can write electron configurations with atomic orbitals, 1s2, 2s2, 2p6, and so on. The same way we can do that, we can translate this diagram into an electron configuration as well. Well, not this one because this doesn't reflect reality, but this one. We could say that the electron configuration for the C2 molecule is sigma 2s 2, and I'll put parentheses around it, followed by sigma 2s star, 2 electrons in there, followed by pi 2p, and we've got 4 electrons in there. And there you go. There's an electron configuration for a molecule. So I have this chart that shows you the electron configurations for a bunch of molecules, some of which are hypothetical, of course, and may not exist in nature. You'd have to force them into existence in the lab, and you'd have to put in energy to stabilize them. They even mark the beryllium molecule and the neon molecule as being unstable. Yeah, I wouldn't expect neon to bond with neon for the same reason I don't expect helium to bond with helium. If you calculate the bond order, which they did in that chart, it's 0. And there's a bunch of electron configurations. I think well, I do have a couple of molecular orbital theory questions in case you want to practice with them, but I'm not going to cover them. I think this video has gone on for long enough already. Maybe I'll cover them in a separate video if I feel the need to and there is the demand, but I think this is where I'm going to stop for today. So let me just show off those problems in case you want to look at them. Here's one set. Next set is this one. Next set is this one. And the final set is this one. So most of it is just, calculate the bond order, write the electron configuration. I don't know if your instructors are going to ask you to go that far. Usually they know that molecular orbital theory is a lot of material to absorb, and they won't set extremely high expectations unless you're going to one of those elite colleges maybe. But, whatever you can remember from this stuff, give yourself a pat on the back, because this is the stuff of nightmares. I don't think it has to be that difficult, but the way that it's just kind of shoehorned into the end of the chapter, it's like drinking water from a fire hydrant. But if you take the time to really get to know it, it's not too horrible. I just wish they would hold off and wait until they ensured that their students had a lot more experience with math, because then you would be way better equipped to understand this stuff. I mean, if you don't know your math, even when you do this right, it feels like when you do your taxes. You don't know if you did it right. You feel uncomfortable and relieved at the same time whenever you're done with it, and it's a weird feeling. So, yeah, don't get too disheartened if this material is hard to take in. Try looking at it over again, maybe 2-3 times, and maybe keep track of what you can remember between watching and re-watching this video or any other source that you might be looking towards for guidance on this topic. Maybe just before you review, write down what stuff you do remember and compare it with what you see when you do your review. I think that'll help you kind of better detect the areas of difficulty that you're having, so that you can focus just on the parts that you're really not getting, and don't sell yourself short for the parts you are getting. But yeah, that's all my advice regarding molecular orbital theory. Congrats to you for making it this far into the video. And yeah, it's messy stuff, but it's not impossible. Through hard work and dedication, you can wrap your head around it, at least partially, until you get to higher math classes. Then maybe you can come back and look at this 3 years after you're done with chemistry and never want to see another chemistry course again. But I've been rambling for too long. Let's just call it a night here. This has been Al the Tutor, reminding you once again that ignorance is not bliss. Take care, and I'll see you in the next video.